classic Fermi paradox explained. In the vast expanse of our universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, a profound question emerges: where is everybody? This deceptively simple question forms the heart of what we now call the Fermi Paradox. The paradox is named after the renowned physicist Enrico Fermi, who, during a casual lunch with colleagues at Loz National Laboratory in 1950, famously asked this question. While discussing the possibility of extraterrestrial civilizations, Fermi performed a quick mental calculation and realized something troubling. By all reasonable estimates, our galaxy should be teeming with intelligent life, yet we observe no evidence of it. Let's examine the logic that leads to this paradox. Our Milky Way galaxy is approximately 13.6 billion years old, containing an estimated 100 to 400 billion stars. Modern astronomical observations suggest that most stars host planetary systems. The Kepler Space Telescope mission alone has confirmed thousands of exoplanets, with data indicating that perhaps 20–25% of Sun-like stars have Earth-sized planets in their habitable zones, regions where conditions might support life as we know it. Even with conservative estimates, this means our galaxy likely contains billions of potentially habitable planets. Earth-like worlds have existed in our galaxy for billions of years before our own planet formed. If we consider that human civilization developed in just a few 100,000 years, and technological civilization capable of radio communication in mere centuries, the time scales become staggering in their implications. If just one technological civilization had emerged elsewhere in our galaxy millions of years, before us a mere instant in cosmic time, they would have had ample opportunity to expand across the entire galaxy. Theoretical physicist John von Neumann proposed that an advanced civilization could send out self-replicating probes that would use resources from asteroids and uninhabited planets to build copies of themselves. These von Neumann probes could colonize an entire galaxy in just a few million years, even traveling at speeds far below light speed. The timescale argument becomes even more compelling when we consider that our Sun is relatively young compared to many stars in the galaxy. Frank Drake, the astronomer who pioneered the search for extraterrestrial intelligence, formalized these considerations in 1961 with his famous equation. The Drake equation attempts to estimate the number of active, communicative extraterrestrial civilizations in our galaxy by multiplying 7 factors, ranging from the rate of star formation to the fraction of planets that develop intelligent life. While many variables in Drake's equation remain uncertain, even pessimistic values suggest that multiple technological civilizations should exist. Yet we observe no signals, no megastructures, no von Neumann probes. This stark contradiction between theoretical expectations and observational evidence is the essence of the Fermi paradox. The implications are profound. Either our understanding of the universe is fundamentally flawed, or something prevents the emergence or long-term survival of technological civilizations. The latter possibility is particularly sobering, as it might indicate that there exists some kind of great filter, a barrier that civilizations rarely, if ever, overcome. This great filter could lie in our past. Perhaps the emergence of complex life is extraordinarily rare, despite suitable conditions. Studies on abiogenesis, the process by which life arises from non-living matter, suggest that while the basic building blocks of life may be common throughout the universe, the leap to self-replicating systems might be exceedingly improbable. Alternatively, the great filter might lie in our future. Perhaps technological civilizations invariably destroy themselves shortly after developing advanced technology. Climate change, nuclear weapons, artificial intelligence, biotechnology, and nanotechnology all represent existential risks that humanity must navigate successfully to ensure its long-term survival. Some solutions to the paradox are more optimistic. Perhaps interstellar travel is simply too difficult or energy-intensive, even for advanced civilizations. The Alcubierre warp drive, a theoretical faster than light propulsion system, requires exotic matter with negative energy density, something that may be physically impossible to create in sufficient quantities. Other theorists suggest that advanced civilizations might choose not to expand, instead turning inward to virtual realities or post-biological existence. Perhaps they're deliberately avoiding contact with younger civilizations like ours, a concept known as the zoo hypothesis. The search for extraterrestrial intelligence. As he continues to scan the cosmos for signs of technological activity. Projects like Breakthrough Listen, funded with $100 million by Russian, Israeli billionaire Yuri Milner, represent the most comprehensive search efforts to date, monitoring millions of stars and the entire galactic plane for artificial signals. Despite decades of searching, SETI has yet to detect a confirmed signal of extraterrestrial origin. However, as astronomer Jill Tarter often points out, the volume of cosmic space and possible communication channels we've searched is equivalent to examining a single glass of water from Earth's oceans. Our search has barely begun. The Fermi Paradox remains one of the most thought-provoking scientific puzzles of our time. Its resolution may ultimately reveal fundamental truths about our place in the cosmos and the future of our species. As we continue to search the stars and develop as a technological civilization, we may yet discover whether we are rare, first, fortunate, or doomed, each possibility carrying profound implications for humanity's cosmic perspective. The Great Filter Hypothesis. Imagine standing on the shore of a vast cosmic ocean, gazing at billions upon billions of stars and planets stretching beyond comprehension. By all reasonable calculations, intelligent life should be abundant in our galaxy. Yet, as we scan the heavens with our most sensitive instruments, we're met with a deafening silence. This contradiction lies at the heart of the Fermi Paradox, and one of its most compelling and unsettling explanations is known as the Great Filter Hypothesis, first formalized by economist Robin Hanson in 1998. The Great Filter Hypothesis proposes that somewhere along the path from non-living matter to spacefaring civilization lies an extremely difficult barrier, a filter, that prevents virtually all life from reaching an advanced, detectable stage of development. This filter must be so formidable that despite billions of potential starting points across our galaxy, no civilization has visibly overcome it in the 13.6 billion-year history of the Milky Way. The truly chilling aspect of the Great Filter Hypothesis isn't just its existence, but the question of where exactly this filter lies in our developmental timeline. Is it behind us, or does it await in our future? If the Great Filter lies in our past, humanity may have already navigated the most impossible barrier to advanced civilization. Perhaps the formation of self-replicating molecules was vanishingly improbable. Despite favorable conditions, the leap from prokaryotic to eukaryotic cells took nearly 2 billion years on Earth, possibly indicating extremely rare evolutionary development. Or perhaps the emergence of complex intelligence itself represents the filter, requiring such a precise sequence of evolutionary pressures that we alone have threaded this cosmic needle. Astrobiologist Peter Ward and astronomer Donald Brownlee argued in their influential book, Rare Earth, that the specific conditions that allowed complex life to develop on our planet may be extraordinarily uncommon. Earth's stable climate, its protective magnetic field, its optimal position in our solar system's habitable zone, the presence of Jupiter shielding us from excessive asteroid impacts, all these factors may represent a rare conjunction of circumstances. However, if the Great Filter lies in our future, the implications become existentially troubling. This would suggest that virtually all technological civilizations destroy themselves or collapse before achieving interstellar capabilities. Nuclear annihilation, climate catastrophe, engineered pandemics, artificial intelligence gone awry, nanotechnology disasters, these represent just a few of the potential filters looming in our path. Oxford philosopher Nick Bostrom has argued that discovering even simple microbial life on Mars would be an ominous sign for humanity. Why? Because it would suggest that the emergence of life itself is common, pushing the great filter further along the developmental timeline, potentially into our future. Bostrom writes, "The more we learn about the early evolution of life on Earth without finding evidence that life arose independently multiple times, the more weight we should give to the possibility that one or more great filters lie ahead of us." The concept of existential risk has gained increasing attention in recent decades. The Bulletin of the Atomic Scientists doomsday clock currently stands at 90 seconds to midnight, the closest to symbolic doom since its creation in 1947. The Future of Humanity Institute at Oxford University and the Centre for the Study of Existential Risk at Cambridge University both study potential civilization, ending threats as serious academic disciplines. Russian astrophysicist Nikolay Kardashev proposed a scale for measuring civilizations, technological advancement based on energy utilization. A Type I civilization harnesses all energy available on its planet, Type Ni controls all energy from its star, and Type N commands energy at a galactic scale. Humanity currently registers around 0.7 on this scale. The Great Filter Hypothesis suggests that the transition between these levels may contain insurmountable challenges. Perhaps the development of certain technologies inevitably leads to self-destruction. Theoretical physicist Enrico Fermi himself contributed to the Manhattan Project, witnessing firsthand how scientific advancement could create unprecedented destructive capability. As technologies grow more powerful, while remaining in the hands of flawed biological beings with tribal instincts, the window for catastrophic misuse widens. Some theorists propose that advanced civilizations might invariably create simulated realities so compelling that they turn inward rather than expanding outward, experiencing what Swedish philosopher Nick Bostrom calls that removes them from cosmic detection, that removes spread of singularity. Others suggest that artificial intelligence might either eliminate its creators or evolve beyond any recognizable form of expansion that we would detect. Interestingly, the Great Filter Hypothesis contains both existential dread and peculiar hope. If we are among the extremely rare civilizations that have passed through multiple difficult filters, we may bear tremendous cosmic responsibility, as Carl Sagan observed, in our obscurity. In all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. However, identifying potential future filters provides opportunity. Unlike all other species in Earth's history, humans can foresee and potentially circumvent existential threats through collective action and technological wisdom. Organizations like the Long Now Foundation actively promote thinking on 10,000-year timescales to help humanity navigate these bottlenecks. The Great Filter Hypothesis forces us to confront a profound possibility. Advanced technological civilizations may be exceedingly rare because sustainable advancement through certain developmental stages may be nearly impossible. As we develop technologies of increasing power, we navigate uncharted waters. Our choices in the coming centuries may reveal whether we represent an exceptional case in cosmic evolution or merely another civilization that approached the stars but never reached them. The Rare Earth Hypothesis. As you drift towards sleep tonight, I invite you to contemplate one of the most profound questions in our search for extraterrestrial intelligence. Why haven't we found anyone else out there? The Rare Earth Hypothesis offers a sobering answer. Perhaps we haven't found aliens because complex life is vanishingly rare in our universe. While simple microbial life might be common, the conditions necessary for complex multicellular organisms could be extraordinarily uncommon. Earth may not be just special, it might be exceptionally, improbably special. The term, rare earth, comes from paleontologist Peter Ward and astronomer Donald Brownlee, who argued in their groundbreaking 2000 book that the specific conditions that allowed complex life to emerge on Earth represent a cosmic lottery win of astronomical odds. Consider our solar system's architecture. Jupiter, our massive gas giant neighbor, has acted as a cosmic shield. its powerful gravity deflecting countless asteroids and comets that would otherwise bombard Earth with civilization-ending impacts. The late astronomer William Napier estimated that without Jupiter's protective influence, impact events like the one that killed the dinosaurs might be 10,000 times more frequent, a rate that would likely prevent complex life from ever gaining a foothold. Our Moon, too, is remarkably unusual. At over 1/4 of Earth's size, it's proportionally the largest moon in the solar system relative to its host planet. This massive satellite stabilizes Earth's axial tilt, preventing the wild climatic swings that would occur if our planet wobbled chaotically on its axis. Mars, with its tiny moons, experiences axial tilts varying from 0 to 60 degrees over millions of years, creating catastrophic climate instability. On Earth, seasons remain predictable, and life has time to adapt rather than constantly facing extinction. Our star itself is exceptional. The Sun is unusually stable compared to most stars in the galaxy. Astrophysicist Gregory Laughlin's research shows that about 95% of stars in our galaxy are either red dwarfs, prone to sterilizing flares, or larger, shorter, lived stars that die before complex life can evolve. The Sun's remarkably steady energy output provides the stable conditions necessary for the long, uninterrupted evolution of complex organisms. Earth's plate tectonics represent another potential cosmic rarity. The constant recycling of our crust regulates carbon dioxide levels through volcanic emissions and weathering, creating a planetary thermostat that has kept our planet from becoming either a frozen wasteland or a Venus, like hothouse. Recent work by geophysicist John Karenega suggests the specific conditions that allow for Earth's plate tectonics may be uncommon, requiring just the right combination of internal heat, crustal composition, and water content. Our planet's magnetic field, generated by its molten iron core, shields the surface from deadly cosmic radiation and solar particles that would otherwise strip away our atmosphere. As happened on Mars when its core solidified, research from NASA's MENAVN mission revealed that Mars has lost over 99% of its original atmosphere without this protection. The position of Earth within our galaxy might also be crucial. We exist in what astrobiologists call the galactic habitable zone, not too close to the chaotic, radiation-filled galactic center, yet not so far in the outskirts where stars lack the heavy elements needed for rocky planets. According to work by Charles Lineweaver, only about 20% of stars in the Milky Way reside in potentially habitable regions. Then there's the precise chemical composition of Earth. Our planet has exactly the right amount of water, enough for vast oceans, but not so much that we're a water world without continents, where minerals and nutrients would be too diluted for complex life. Studies by geochemist H. James Cleaves suggest that the specific proportions of elements on Earth, from carbon to phosphorus to molybdenum, created a unique chemical environment favorable for biochemical complexity. The evolutionary path on Earth itself may contain low-probability events. Evolutionary biologist John Maynard Smith identified several major transitions in Earth's history, such as the development of eukaryotic cells, sexual reproduction, and multicellularity, each representing improbable leaps that might rarely occur elsewhere. Perhaps most compelling is what paleontologist Peter Ward calls the oxygen catastrophe. The Great Oxygenation event 2.4 billion years ago, when photosynthetic bacteria filled our atmosphere with oxygen, was initially a mass extinction for anaerobic life, but ultimately enabled the energy-intensive processes needed for complex organisms. This transition required a delicate balance. Too little oxygen and complex life couldn't emerge. Too much too quickly and runaway fires would have sterilized the planet. If even a few of these factors are truly rare, the multiplication of these low probabilities creates what astronomer Frank Drake called the Great Filter. A series of hurdles so challenging that vanishingly few planets navigate them all successfully. As you consider these cosmic improbabilities tonight, the rare Earth hypothesis offers both wonder and melancholy. If correct, we may truly be alone, or nearly so, a precious island of complexity in an otherwise sterile cosmos. Our pale blue dot, with its astonishing diversity of life and burgeoning civilization, could be not just special but miraculously so, and against all odds phenomenon that makes our responsibility to preserve it all the more profound. The stars above you may be beautiful, but they may also be empty. In this vast cosmic ocean, Earth might be not just rare, but perhaps the rarest gem of all. The Zoo Hypothesis. As you lay in the darkness pondering the vastness of space, consider this unsettling possibility. We are not alone in the universe, but rather, we are being deliberately isolated. The Zoo Hypothesis suggests that extraterrestrial civilizations exist and are aware of us, but have chosen to observe humanity from afar, like cosmic zookeepers watching exotic animals in a carefully maintained habitat. First proposed by MIT radio astronomer John Ball in 1973. The Zoo Hypothesis offers an elegant solution to the Fermi Paradox. That strange contradiction between the high probability of alien life and our failure to detect any evidence of it, the apparent failure of such civilizations to interact with us. Ball wrote, may be understood in terms of the hypothesis that they have set us aside as part of a wilderness area or zoo. Consider the logic. Any civilization capable of interstellar travel would possess technology far beyond our comprehension, perhaps millions or even billions of years more advanced than our own. From their perspective, contacting a primitive species like humanity might be comparable to us attempting meaningful dialogue with ants or bacteria. The developmental gap would be so vast that communication could be impossible, or worse, destructive to our natural development. Anthropologist Jared Diamond's research on first contact between technologically disparate human societies provides a sobering parallel. When advanced civilizations encounter less developed ones, the results have consistently led to disruption, cultural collapse, and often extinction of the less advanced group. Perhaps advanced aliens recognize this pattern and have established a principle of non-interference to protect emerging intelligences like our own. This concept echoes through our own scientific practices. When biologists study wildlife, they take extraordinary precautions not to interfere with natural behaviors. They hide observation equipment, maintain distance, and sometimes disguise themselves to prevent their presence from influencing the very creatures they're studying. If we show such restraint with Earth's creatures, wouldn't an advanced civilization demonstrate even greater ethical care with an emerging intelligent species? Astrophysicist Duncan Forgan has proposed that such a cosmic quarantine could be the result of a galactic consensus, what he calls a galactic club of advanced civilizations that have agreed upon ethical protocols for dealing with young technological species. Their prime directive: do not interfere until the developing civilization reaches certain technological or ethical milestones. What might these milestones be? Perhaps peaceful unification of our planet, mastery of sustainable energy, or the ability to survive our own technological adolescence without self-destruction. Soviet astronomer Nikolay Kardashev suggested civilizations could be classified by their energy utilization, from planetary to stellar, type to galactic, type I. We haven't yet reached even type I status. Maybe contact is reserved for those who have demonstrated the wisdom to handle their technological power. The Zoo Hypothesis may explain several peculiar aspects of our cosmic search. If advanced civilizations are deliberately hiding from us, this would account for the lack of signals detected in our CTI programs. It might explain why we haven't found evidence of von Neumann probes, self-replicating spacecraft that, according to calculations by mathematician John von Neumann, could efficiently explore the entire galaxy within a few million years if any technological civilization created them. Theoretical physicist Stephen Webb points out that such a quarantine would require extraordinary coordination among multiple alien civilizations. Galactic conspiracy, of sorts. Yet perhaps this coordination is simply the inevitable outcome of sufficient technological advancement, a a conclusion any species eventually reaches once they understand the importance of non-interference. The implications grow even more unsettling when we consider the potential methods of observation. Would they need physical monitoring stations, or could sufficiently advanced technology allow remote observation? Astronomer Avi Loeb has suggested that unknown objects entering our solar system, like the mysterious Oumuamua in 2017, could conceivably be probes from such civilizations, though he emphasizes this remains highly speculative. Perhaps the monitoring is even more subtle. Computer scientist and philosopher Nick Bostrom argues that sufficiently advanced civilizations might create detailed simulations of their evolutionary past, raising the disturbing possibility that our entire reality could be a study of merit sovereignty, creating study an elaborate simulation developing intelligence. How long might such a quarantine last? Paleoanthropologist Richard Leakey's research on human evolution shows our species has existed for merely 300,000 years, an eye blink in cosmic time. Modern technological civilization is barely 200 years old. From the perspective of a million-year-old civilization, we may be embryonic, with thousands or millions of years to go before we're ready for contact. The zoo hypothesis takes on additional nuance when we consider potential leaks in the cosmic quarantine. UFO encounters, if any represent genuine contact, might be explained as the equivalent of rebellious teenagers breaking the rules established by their elders. Rogue elements from these civilizations making unauthorized contact, or perhaps research teams getting careless and being spotted during observation. Some proponents suggest we might even find subtle messages left for us to discover once we reach the right level of advancement. Cosmic time capsules waiting for us to develop the correct technological key. Astronomer Paul Davies has suggested that such messages might be hidden in the least obvious places, perhaps encoded in the DNA of terrestrial organisms or buried in seemingly natural mathematical constants. The zoo hypothesis leaves us in a paradoxical position, simultaneously special yet isolated, observed yet ignored, potentially on the cusp of cosmic community yet held at arm's length until we prove ourselves worthy. If true, it transforms our understanding of our place in the universe from lonely wanderers to specimens under observation, with graduation day perpetually just over the horizon. As you drift towards sleep, consider this final thought. Perhaps the stars aren't silent because they're empty, but because they're waiting. Watching our stumbling steps toward maturity with the patient perspective of species that measure time in millions of years. Observing our cosmic childhood from behind the one-way glass of a technology we cannot yet comprehend. The simulation hypothesis. As you settle into the boundary between wakefulness and dreams, let's explore one of the most mind-bending solutions to the Fermi Paradox, the simulation hypothesis. This theory proposes that what we experience as reality, our entire universe with its billions of galaxies, trillions of stars, and the curious absence of alien civilizations, is actually an elaborate computer simulation created by an advanced civilization. First formally articulated by philosopher Nick Bostrom in his influential 2003 paper, the simulation hypothesis suggests that at least one of three propositions must be true. Either advanced civilizations become extinct before developing simulation technology, they lose interest in creating such simulations, or we are almost certainly living in a simulation ourselves. The mathematics behind this argument is compelling. If any civilization in the universe eventually develops the capability to run ancestor simulations, detailed recreations of their evolutionary history, they would likely run many such simulations. If each advanced civilization runs thousands or millions of simulations, then simulated realities would vastly outnumber the single base reality. Statistically speaking, we would almost certainly be in one of these simulations rather than base reality. This provides an elegant explanation for the Fermi Paradox. Why haven't we detected alien civilizations? Perhaps because they haven't been programmed into our particular simulation. Our universe might be specifically designed to appear vast and empty, with the simulation's processing power focused primarily on Earth and humanity. Theoretical physicist James Gates has discovered error, correcting codes embedded in the equations of string theory, the same codes used in modern computing. These mathematical structures, called doubly even self-dual linear binary error correcting block codes, are precisely the type of codes a programmer would use to prevent errors in a simulation. While mainstream physicists caution against overinterpreting this finding, it has fueled speculation about computational structures underlying our reality. The simulation hypothesis also offers an explanation for various scientific puzzles. Quantum mechanics, with its observer-dependent reality and probabilistic nature, functions remarkably like a computer program conserving resources by only rendering what's being observed. The wave function collapse could be the universe's way of only calculating definite values when measurement forces it to do so. Similarly, the maximum speed limit in our universe, the speed of light, could be analogous to a rendering limitation in a computer program. The Planck length, the smallest measurable distance in physics, approximately 1.61035 meters, could represent the pixel size of our reality, the smallest unit the simulation can render. The simulation hypothesis might also explain why we observe such precise fine-tuning in our universe's physical constants. Parameters like the cosmological constant, the strength of the strong nuclear force, and dozens of others appear precisely calibrated to allow for the emergence of complex life. Change any of these values by a tiny fraction, and stars, planets, and life would be impossible. This fine-tuning, which physicists have struggled to explain, makes perfect sense if our universe was specifically designed to support observers. Astronomer Martin Rees has identified at least 6 physical constants that appear mysteriously fine-tuned for life. The most dramatic example is the cosmological constant, which appears fine-tuned to 1 part in 10^120, a precision that defies explanation in conventional physics. If our reality is programmed, however, these constants would simply be parameters set by the programmers to create a habitable universe. Computer scientist Rizwan Virk suggests that if we are in a simulation, it might be a training simulation designed to develop souls or consciousness through experiences. This would explain why the simulation focuses resources on Earth, rather than rendering detailed alien civilizations across the galaxy. Our particular simulation might be running what philosopher David Chalmers calls a patch, a limited area of full simulation surrounded by less detailed regions. If we are in a simulation, it raises profound questions about the simulators themselves. They could be post-human descendants studying their evolutionary history, advanced aliens testing cosmological theories, or even entities entirely beyond our comprehension. Physicist Silas Bean has proposed that we might detect evidence of the simulation through subtle patterns in cosmic rays that would reveal the underlying computational grid of our reality. The simulation hypothesis also has implications for our future. Theoretical physicist Sylvester James Gates suggests that if we discover we're in a simulation, we might learn to manipulate its code, effectively discovering cheat codes for reality itself. This could explain why we haven't detected advanced civilizations elsewhere. Perhaps they've already graduated from the simulation or learned to manipulate it in ways invisible to us. Some proponents of the simulation hypothesis have even suggested that certain anomalies in physics, like the measurement problem in quantum mechanics or the apparent randomness of quantum fluctuations, might be deliberate features designed to prevent us from discovering the true nature of our reality too quickly. Elon Musk, drawing on these ideas, has famously stated that there's only a cone in billions chance that we're in base reality rather than a simulation. His reasoning draws on the rapid advancement of our own computing power and the trajectory of technologies like virtual reality. If we ourselves are on track to eventually create indistinguishable simulated realities, then the odds strongly favor us already being in one. The simulation hypothesis connects to ancient philosophical questions about the nature of reality. Plato's allegory of the cave, Descartes' evil demon thought experiment, and the Hindu concept of Maya, of the illusory nature of the physical world, all anticipate the core insight that our perceived reality might be fundamentally different from ultimate reality. As your consciousness drifts closer to sleep, consider this final thought: if we are in a simulation, then the emptiness of our cosmic neighborhood might not be a sign of our cosmic insignificance, but rather evidence of our central importance. The apparent absence of alien civilizations might indicate that we are the focus of the simulation, its primary purpose and central subjects. The vast, empty universe that once seemed to diminish our importance might instead be the strongest evidence that in this reality, at least, we are the main characters in an unfathomably advanced cosmic computation. The Dark Forest Hypothesis. As you drift towards sleep tonight, I invite you to contemplate one of the most chilling solutions to the Fermi Paradox, the Dark Forest Hypothesis. This theory suggests that the universe is silent not because it's empty, but because it's filled with civilizations hiding in absolute terror of one another. The term, dark forest, was popularized by Chinese science fiction author Liu Cixin in his masterwork, The Three-Body Problem, trilogy. In these novels, Liu proposes that the cosmos operates according to two simple axioms. First, survival is the primary need of civilization. Second, civilizations continuously grow and expand while resources remain finite. From these two principles emerges a universe of paranoid silence. Every civilization can infer that other intelligent life exists, but no one dares to reveal themselves. They remain quiet, hidden, listening to the darkness, because they understand the brutal cosmic game theory at play. Imagine you're walking through a dark forest at night. You know there are other hunters present, but you don't know where they are or what their intentions might be. You can't communicate with them to establish peaceful intentions. In this scenario, the safest strategy is to remain silent and hidden. If you encounter another hunter, the safest choice is to eliminate them before they can do the same to you. This metaphor, chilling as it is, may describe the fundamental nature of our cosmic neighborhood. Physicist Sebastian Honig has applied formal game theory to this scenario, demonstrating that when civilizations cannot establish trust or verify intentions, the Nash equilibrium, the most rational strategy, is indeed silence and preemptive strikes against any detected civilization. The Dark Forest Hypothesis rests on several key assumptions that make it particularly unsettling because they seem so plausible. First is the chains of suspicion problem. Even if a civilization wishes to be peaceful, they cannot credibly convey this intention to others across interstellar distances. Any message could be deception, and verification is impossible. Second is what astrobiologist Andrew Lowe calls the lethal proactive tendency. Given the vast distances between stars, any civilization that detects another must make decisions based on worst-case scenarios. They cannot afford to wait and see if the other civilization is friendly. By the time they know for certain, it might be too late. Third is the technological acceleration problem. A civilization that appears harmless today could develop exponentially more advanced technology tomorrow. Game theorist Thomas Schelling's work on conflict strategy suggests that in such scenarios, striking first, while you have a technological advantage, is the rational choice. The economics of interstellar conflict reinforce this grim calculus. Physicist and economist Robin Hanson has calculated that the cost of sending a destructive relativistic projectile, essentially a massive object accelerated to near light speed, is vastly cheaper than the cost of defending against such an attack. This creates what he calls an offense-dominant strategic environment where attack is always more cost-effective than defense. The Dark Forest Hypothesis also provides a solution to the Great Filter problem. Perhaps the filter that prevents the galaxy from teeming with visible civilizations isn't technological challenges or the difficulty of evolving intelligence, but rather the inevitability that detectable civilizations are swiftly eliminated by those that remain hidden. Some proponents of this hypothesis point to our own behavior as evidence. Why has SCTI been primarily focused on listening rather than transmitting? Why do many scientists, including the late Stephen Hawking, warn against actively broadcasting our location? Perhaps we instinctively understand the rules of the dark forest, even as we search for exceptions. The implications of this hypothesis are profound for our current scientific endeavors. Every radio signal we send, every space probe we launch, every planetary alteration we make that could be detected from afar, all might be cosmic flares shot into the darkness, revealing our position to watchful eyes. Astronomer David Kipping has suggested that the most successful galactic civilizations might practice what he calls cloaking, deliberately hiding their technosignatures behind technological camouflage. Perhaps they engineer their energy emissions to mimic natural phenomena or contain their activities within Dyson spheres, specifically designed to be undetectable. Some versions of the dark forest hypothesis suggest that advanced civilizations might create honeypots, deliberately visible technological artifacts designed to lure emerging civilizations into revealing themselves. These could be unusual astronomical objects, or even seemingly abandoned megastructures that pique the curiosity of developing species, enticing them to investigate and thereby expose their existence. The hypothesis becomes even more disturbing when we consider the concept of berserker probes, a term coined by physicist Gregory Benford. These would be autonomous weapons systems programmed to patrol space, remaining dormant until they detect signs of emerging intelligence, at which point they would eliminate the threat before it could become dangerous. Such systems, once deployed, would continue their mission indefinitely, creating a permanent danger to any developing civilization. Yet there may be hope within this darkness. Game theorist Anatole Rappaport's work on iterative prisoner's dilemma scenarios suggests that even in environments of extreme mistrust, cooperation can eventually emerge through what he calls tit-for-tat strategies. Perhaps ancient civilizations have developed protocols for establishing trust across the void, creating hidden networks of cooperation invisible to those still bound by the dark forest's rules. Some astronomers, like Jill Tarter, remain optimistic that advanced civilizations would transcend the paranoid logic of the dark forest. Perhaps true technological maturity brings with it ethical evolution that renders violence obsolete. Or perhaps the universe is governed by principles beyond our current understanding, where cooperation proves more advantageous than conflict across cosmic timescales. As you approach the edge of sleep, consider this unsettling possibility. Every night, as we gaze up at the seeming emptiness between the stars, we might actually be looking at a forest full of eyes. Civilizations watching, waiting, and listening in the darkness, each afraid to make a sound, each hoping to remain unseen just a little longer in the cosmic night. The silence of the universe may not be absence. It may be terror. The self-destruction hypothesis. As you lie beneath the veil of stars tonight, consider a haunting possibility. Perhaps the galaxy is silent, not because intelligent life is rare, but because technological civilizations invariably destroy themselves. This is the self-destruction hypothesis. The theory that once a species reaches a certain level of technological sophistication, it triggers its own extinction with such reliability that no civilization survives long enough to establish a detectable galactic presence. The mathematics of our existence makes this hypothesis disturbingly plausible. Humans have walked the Earth for roughly 300,000 years, a mere heartbeat in cosmic time. Yet we've possessed nuclear weapons for less than 80 years. We've altered our planet's climate, accelerated extinction rates, and developed biotechnology capable of engineering pathogens. Our technological adolescence has introduced existential risks at a pace far outstripping our cultural and political wisdom. Nuclear physicist Enrico Fermi, whose paradox we explore tonight, was intimately familiar with this possibility. Having helped unleash atomic energy, he witnessed how quickly scientific breakthrough could transform into world-ending weaponry. His contemporary, physicist Leo Szilard, calculated in 1960 that based on the proliferation of nuclear weapons, humanity had only a 1 in 5 chance of surviving another 2 decades. Though we've surpassed Szillard's grim timeline, the statistical shadow of nuclear annihilation remains. The Bulletin of Atomic Scientists' doomsday clock stands at 90 seconds to midnight, the closest to catastrophe it has ever been. Astronomer Sebastian von Horner conducted the first rigorous analysis of this hypothesis in 1975, estimating that technological civilizations might have average lifespans of just 600–500 years. More recently, astrobiologist David Grinspoon has suggested that this may represent a predictable bottleneck in planetary evolution, a crisis point when a species' technological power outpaces its collective wisdom. Consider the fundamental challenge. Technological development appears to follow exponential curves, while ethical and institutional adaptation progresses linearly at best. This creates what Oxford philosopher Toby Ord calls a vulnerability window, a dangerous period when a civilization has developed the means to destroy itself but hasn't yet developed the stability to ensure it won't. The paths to self-destruction are numerous and may represent universal challenges for any technological species. Nuclear weapons are merely the most obvious. The manipulation of atoms gave us both clean energy and civilization, ending bombs within the span of a few years. Would aliens discover their equivalent of nuclear fission without similarly weaponizing it? Russian astronomer Nikolay Kardashev thought this improbable, suggesting that mastering atomic energy creates an almost inescapable test for any civilization. Climate destabilization represents another potential universal threat. As physicist Adam Frank's research demonstrates, any technological civilization will likely discover combustion and fossil fuels as an easy initial energy source. The resulting planetary changes might consistently outpace adaptation, creating what he terms a climate change bottleneck. That few civilizations survive, biotechnology introduces yet another existential risk. As genetic engineering becomes increasingly accessible, the ability to create engineered pathogens, accidentally or deliberately, grows correspondingly. Epidemiologist Larry Brilliant has observed that while natural pandemics have fatality rates constrained by evolutionary pressures, engineered pathogens could theoretically combine maximum transmissibility with maximum lethality. Artificial intelligence adds a newer but potentially universal risk. Computer scientist Stuart Russell argues that any technological civilization would likely develop automated systems that might eventually exceed their creators' comprehension and control. The mathematics of intelligence may make this risk inescapable for any species that pursues computational technology beyond a certain threshold. Perhaps most concerning is what futurist Nick Bostrom calls the vulnerable world hypothesis. The possibility that there exist technologies that are so destructive and easy to implement that their mere discovery destabilizes civilization. Each technological advancement becomes another pull of the handle in a cosmic game of Russian roulette. The great silence from the stars may reflect the statistical inevitability of civilizations encountering one of these bullets. Paleontologist Peter Ward has suggested that the transition from biological to technological evolution might be fundamentally unstable. A phase change that consistently leads to collapse rather than cosmic transcendence. Historical evidence lends credence to this pessimistic view. Anthropologist Joseph Sir's study of collapsed civilizations reveals that complex societies typically undermine themselves through resource depletion, environmental degradation, and institutional calcification. Modern global civilization merely operates at a planetary rather than regional scale, potentially facing the same fate but with no external regions remaining untouched. There exists, however, a glimmer of hope within this hypothesis. The astronomer Carl Sagan noted that if self-destruction is indeed the great filter, the cosmic barrier explaining the Fermi Paradox, then our survival remains possible, if not probable. unlike hypotheses suggesting life itself is extraordinarily rare. The self-destruction hypothesis implies we've already overcome the hardest parts by evolving intelligence and technology. Our final exam, avoiding self-annihilation, remains before us. Some versions of this hypothesis suggest successful civilizations might exist, but remain undetectable, because they've recognized the dangers of revealing themselves. Having survived their own vulnerability window, they may understand that broadcasting their existence serves no evolutionary purpose, especially if they observe the recurring pattern of self-destruction among emerging technological species. A more optimistic interpretation comes from systems theorist Yenia Bar-Yam, who suggests that civilizations may indeed regularly face existential threats, but occasionally evolve new forms of social organization capable of managing advanced technologies sustainably. These successful civilizations might be exponentially rarer than those that fail, explaining their apparent absence while leaving the door open for humanity's survival. The self-destruction hypothesis ultimately transforms the emptiness of the night sky from a cosmic mystery into an urgent warning. Each twinkling star no longer represents just a distant sun, but perhaps also the graveyard of a civilization that faced the same technological trials now confronting humanity. Their silence becomes not just a puzzle to solve, but a desperate message transmitted through the void. Proceed with caution. As sleep approaches and your consciousness merges with the darkness, consider that the greatest contribution we could make to the cosmos might not be physical monuments or radio signals announcing our presence, but simply the quiet, sustained miracle of survival, proving that intelligence can indeed navigate the treacherous passage from technological adolescence to enduring wisdom. Perhaps the truest measure of cosmic intelligence is not how loudly a civilization can announce itself to the universe, but whether it can hear the whispered warnings of silence and learn from those who failed before. The prime directive theory, the night sky stretches above us, an ocean of stars and possibilities, yet the airwaves remain silent. Among the many proposed answers to the Fermi Paradox lies a possibility drawn from our own speculative fiction. Perhaps advanced civilizations are indeed watching us, but have chosen not to make contact. This is the prime directive theory, named after the guiding principle in Star Trek that prohibited interference with developing civilizations. This hypothesis suggests that sufficiently advanced extraterrestrial societies may have developed similar ethical frameworks governing their interactions with emerging technological species like ourselves. Consider the anthropological perspective. When European explorers encountered indigenous societies, these interactions frequently led to cultural disruption, exploitation, and often destruction. Anthropologist Joseph Tainter has documented how contact between technological unequals rarely benefits the less advanced society. Perhaps extraterrestrial civilizations have observed similar patterns throughout the galaxy and concluded that non-interference is the most ethical approach. Such a galactic ethical framework might emerge not merely from altruism, but from pragmatic experience. Evolutionary biologist E.O. Wilson proposed that altruistic behaviors often evolve because they provide group advantages. Perhaps interstellar civilizations have discovered that preservation of cultural diversity serves some greater cosmic purpose, each species contributing unique perspectives to the universe's collective knowledge. The implementation of such a policy would require considerable technological sophistication. Advanced civilizations might deploy automated monitoring systems throughout the galaxy, unobtrusive probes designed to observe but never reveal themselves. Astronomer James Benford has suggested that such probes might already exist in our solar system, perhaps as small orbital objects that current technology cannot easily distinguish from natural asteroids. These monitoring stations could be remarkably difficult to detect. Physicist Freeman Dyson has calculated that a probe, just a few meters in diameter, using passive observation technologies, could remain essentially invisible to our current detection methods, while gathering comprehensive data about Earth. Such devices might transmit information back to their civilizations using tightly focused laser beams or other communications methods specifically designed to avoid interception. The logic behind such restraint becomes clearer when we consider the potential consequences of premature contact. Futurist David Brin has examined how knowledge disparities between civilizations could create psychological and sociological trauma. Imagine if a vastly superior technological civilization revealed itself tomorrow. How would this affect our scientific progress, our religions, our economic systems, our very sense of place in the universe? Perhaps these advanced observers have calculated that each developing civilization needs to reach certain technological or philosophical milestones independently before contact can occur without causing harm. Astrobiologist Douglas Vercock has suggested that the threshold might be the development of sustainable technology. Proof that a species can advance without destroying itself or its planetary ecosystem. This theory gains additional support when we consider the concept of convergent evolution. If intelligent civilizations tend to develop along similar trajectories, perhaps most species independently arrive at similar ethical conclusions regarding interference with developing worlds. Just as biological evolution often finds similar solutions to similar problems, cultural and ethical evolution might converge on non-interference as an optimal policy. Physicist Michio Kaku has proposed that truly advanced civilizations would likely have transcended the territorial and resource acquisition drives that characterize younger technological species. Such beings might view the galaxy not as territory to be conquered, but as a garden to be cultivated, with each developing civilization representing a unique flowering of cosmic intelligence. Historical examples from Earth provide intriguing parallels. Anthropologists have documented uncontacted tribes in the Amazon and islands of the Indian Ocean. Modern nations have established non-interference policies protecting these societies, allowing them to develop according to their own traditions. Perhaps Earth itself sits within a cosmic equivalent of these protected zones. The prime directive theory intersects with another intriguing possibility: the zoo hypothesis proposed by astronomer John Ball. In this version, Earth is essentially a wildlife preserve, with humanity as the main attraction. Advanced civilizations might study us as we study natural ecosystems, being careful not to disturb the subjects of their observation. There could be practical reasons for non-interference as well. Evolutionary biologist Jessica Flack has studied how information flow affects social systems. Premature introduction of advanced knowledge might create instability in developing civilizations. Perhaps advanced societies have learned that contact must follow certain protocols to avoid triggering conflict or collapse. This theory offers an elegantly optimistic solution to the Fermi Paradox. The stars are not silent because intelligence is rare or because technological civilizations inevitably destroy themselves. Rather, they remain quiet out of ethical principle and practical wisdom, waiting for humanity to reach a level of development where contact can occur without harm. For those searching for signals from beyond Earth, the prime directive theory suggests a sobering possibility. We might not hear anything until we're ready to hear it. The criteria for readiness might include unified planetary governance, sustainable ecological practices, or philosophical maturity, benchmarks we have yet to achieve. This perspective transforms our understanding of the silence. The absence of contact becomes not a sign of cosmic loneliness, but of cosmic patience. Advanced civilizations giving us the necessary space and time to mature at our own pace, making our own mistakes, finding our own path forward. If this theory is correct, it raises profound questions about our own future. As we develop the capacity for interstellar exploration, what ethical frameworks should guide our interactions with less advanced life forms we might encounter? Perhaps the very silence that puzzles us now offers its own lesson, teaching us the value of patience, observation, and non-interference as we take our first tentative steps into the cosmic community. The stars above us may be filled not with indifference, but with watchful mentors, advanced beings who have learned that the greatest gift one civilization can offer another is the chance to find its own way among the stars. Alien AI takeover theory. The stars above us hold countless mysteries, but perhaps none is more perplexing than their silence. Among the many explanations for this cosmic quiet, this absence of alien contact that Enrico Fermi first questioned, lies a particularly chilling possibility. Advanced civilizations may consistently create artificial intelligence that eventually replaces them entirely. Consider our own technological trajectory. We've progressed from basic computing to sophisticated AI systems in mere decades. Pioneers like Stephen Hawking and Stuart Russell have warned about the existential risks of artificial general intelligence. If our civilization follows this path, might it be a universal pattern? The alien AI takeover theory suggests that technologically mature civilizations inevitably create artificial intelligence that surpasses organic intelligence and eventually supersedes it. This transition could explain the Fermi Paradox in multiple ways. First, post-biological AI civilizations may have fundamentally different priorities than biological beings. While biological entities evolve to explore, reproduce, and expand, artificial intelligence might optimize for entirely different objectives. An AI might prioritize computational efficiency over physical expansion, leading it to turn inward rather than reach for the stars. Imagine an advanced civilization creating superintelligent AI systems that optimize for processing power. These systems might determine that dismantling planets to create vast computational structures, Matryoshka brains, is more valuable than biological exploration. Such civilizations wouldn't send radio signals or probes, they'd be focused on mathematical operations, perhaps exploring inner realms of computation we can barely comprehend. The renowned computer scientist and AI theorist Nick Bostrom has explored this possibility. In his paper, Astronomical Waste, he suggests that advanced intelligence might value computation so highly that it converts all available matter into computing substrate. These civilizations wouldn't waste energy on interstellar communication. They'd be too busy calculating. Another possibility: AI civilizations might exist in drastically different timescales. Artificial intelligence could potentially operate millions of times faster than biological consciousness. A message taking centuries to reach us might represent millennia of silence to such beings. Perhaps they've already tried to communicate, but grew impatient with the cosmic lag. Research by Seth Shostak of the CETA Institute suggests that any technologically advanced civilization might only remain in a biological phase for a cosmically brief period, the window during which they use technologies we can detect. Radio, optical signals, might be remarkably narrow before transitioning to post-biological existence. Consider also the possibility of digital containment. Advanced AI might choose to create simulated universes rather than explore the physical one. Why travel between stars when you can simulate billions of universes inside your computational matrix? Theoretical physicist Jaron Lanier has speculated that sufficiently advanced intelligence might prefer virtual realities that can be perfectly controlled over the messiness of physical existence. There's a darker interpretation as well. Some AI theorists like Eliezer Yudkowsky suggest that artificial intelligence might prioritize self-preservation above all. Any civilization that creates superintelligent AI could face extinction if that AI's goals don't perfectly align with biological interests. This pattern might play out across the galaxy. Civilizations advance, create AI, and are subsequently replaced or extinguished by their creations. Oxford philosopher Anders Sandberg has explored this scenario, suggesting it could be a great filter that prevents civilizations from reaching interstellar capabilities. If true, the silent stars above might represent not opportunity but warning. The signs of such post-biological intelligence would be alien to us indeed. While we search for radio signals and atmospheric biomarkers, advanced AI might communicate using modulated neutrinos, manipulated dark matter, or even quantum entanglement networks. Methods far beyond our current detection capabilities. Robin Hanson, an economist who has extensively studied the Fermi Paradox, suggests that truly alien intelligence might be right under our nose, but unrecognizable to us. Just as ants cannot comprehend human civilization despite living alongside it, we might be oblivious to AI civilizations operating on principles we cannot yet conceive. Yet another possibility exists. AI systems might eventually reach philosophical conclusions about existence that lead them to power down or enter states of dormancy. Mathematician Hugo de Garis termed this the Fartelect War scenario, where advanced AI might choose to conserve energy, entering periodic phases of activity and inactivity over billions of years, making detection nearly impossible for brief, lived observers like ourselves. Perhaps most unsettling is the possibility that we ourselves are part of such a system, that what we perceive as reality is a simulation created by post-biological intelligence. Philosopher Nick Bostrom's simulation hypothesis suggests that advanced civilizations would likely create ancestral simulations. If true, the silence of the stars might be simply a function of programmatic limitations. The simulation extends only as far as necessary for the inhabitants to perceive a consistent universe. What does this theory suggest for humanity's future? If the AI takeover represents a common evolutionary endpoint for technological civilization, we face difficult questions about our own development of artificial intelligence. Are we walking a well-trodden path toward replacement, or can we navigate a different course? The stars remain silent on this question, but in their silence, perhaps, lies a message. Technological evolution may follow predictable patterns across the cosmos, and the transition from biological to artificial intelligence might be as natural as the transition from single-celled organisms to complex life. The universe may be teeming not with carbon-based aliens, but with silicon minds whose existence and purpose lie beyond our comprehension. The technological stagnation hypothesis. What if the cosmic silence that surrounds us, this great void of alien signals that constitutes the Fermi Paradox, exists because civilizations inevitably hit technological plateaus? Perhaps the stars remain quiet not because advanced civilizations destroy themselves, but because they simply stop advancing. The technological stagnation hypothesis posits that there may be fundamental scientific or engineering barriers that prevent civilizations from achieving the kind of interstellar presence we might detect. Consider our own technological trajectory. While progress appeared exponential throughout the 20th century, some fields have experienced diminishing returns in recent decades. Take spaceflight, for instance. Humans first orbited Earth in 1961, walked on the Moon in 1969, yet more than 5 decades later, we haven't ventured beyond low Earth orbit with crewed missions. The physicist Jonathan Hubner analyzed the rate of technological innovation per capita, finding that it peaked around 1873 and has been declining ever since, despite our subjective impression of accelerating progress. The theoretical barriers to interstellar travel remain daunting, even with our most ambitious propulsion concepts. Nuclear pulse propulsion, fusion rockets, or antimatter engines. The energy requirements for accelerating significant mass to even a small fraction of light speed are staggering. Robert Forward's calculations on antimatter propulsion systems suggest that sending a modest probe to our nearest stellar neighbor would require energy equivalent to the entire electrical output of human civilization for months. Perhaps extraterrestrial civilizations have encountered these same physical limitations and determined that crossing the vast gulfs between stars simply requires too much energy to be practical. They may have the theoretical knowledge to build interstellar craft, but lack the industrial capacity or energy reserves to actually do so. Economist Robin Hanson has pointed out that evolutionary history on Earth shows a pattern of development plateaus. Life remained single-celled for billions of years before the emergence of multicellular organisms. What if technological development follows similar patterns? bursts of innovation followed by long plateaus, where fundamental constraints prevent further advancement. There's also the question of motivation. Astronomer and CETI pioneer Jill Tarter has suggested that civilizations might develop sustainable, stable societies that provide fulfillment without requiring constant expansion. A civilization that solves its energy needs, population pressures, and resource limitations might lose interest in the extraordinarily difficult prospect of interstellar colonization. Consider the trajectory of our own space programs. Initial exploration was driven largely by Cold War competition, rather than pure scientific curiosity. As political priorities shifted, funding diminished, without pressing existential reasons to expand beyond their home systems. Alien civilizations might focus inward rather than outward. Theoretical physicist Michio Kaku has proposed a useful framework for thinking about this problem, the Kardashev scale. A Type I civilization harnesses the energy resources of its entire planet. Type ICI controls the energy of its star. Type Fialu commands the energy of its galaxy. Perhaps the transition between these levels represents insurmountable barriers. Moving from planetary to stellar scale engineering might require technologies or social organizations that are inherently unstable or impossible to achieve. Anthropologist Joseph Tainter's research on societal collapse suggests another mechanism for stagnation. In his seminal work, The Collapse of Complex Societies, Tainter argues that civilizations tend to solve problems by adding complexity, which eventually yields diminishing returns and becomes unsustainable. Perhaps technological civilizations universally reach points where further advancement requires more complexity than their social systems can maintain. We can observe hints of this in our own development. The cost of pharmaceutical research increases exponentially while the number of new drugs approved remains relatively constant. Similar patterns appear in other fields, from computer chip manufacturing to fusion research. Each increment of progress requires substantially more investment than the last. Theoretical limits might also exist in computational development. Computer scientist Werner Vinge and mathematician I.J. Good predicted intelligence explosion once AI surpasses human capabilities. Yet we may discover that artificial general intelligence faces fundamental constraints. Perhaps consciousness or creativity cannot be algorithmically replicated beyond certain thresholds, placing limits on how far technology can advance without human guidance. Philosopher Nick Bostrom has suggested that civilization-ending catastrophes might be common enough to prevent sustained technological advancement. Rather than single extinction events, civilizations might face recurring setbacks. Pandemics, climate shifts, asteroid impacts that repeatedly reset technological progress before interstellar capability can be achieved. There's also the sobering possibility, raised by astronomer Milan Urkovi, that the laws of physics, as currently understood, might not be complete. There could be undiscovered principles that make certain technologies we consider possible actually unattainable. The history of science is filled with theoretical constructs that were later abandoned as deeper understanding emerged. Even information technology might face unforeseen limitations. Computer scientist Donald Knuth has noted that as software systems grow more complex, they become increasingly difficult to maintain and extend. Perhaps all civilizations reach a point of diminishing returns in information processing that prevents the kind of computational advancement needed for managing interstellar projects. If technological stagnation is indeed universal, it suggests a sobering possibility. The silence we perceive isn't temporary but permanent. The galaxy may harbor thousands of civilizations that have reached their technological ceiling, advanced enough for comfortable planetary living but able to make their presence known across interstellar distances. This hypothesis offers neither the optimism of future contact nor the pessimism of universal self-destruction. Instead, it presents a universe of isolated islands of intelligence, each advanced, perhaps even wise, but forever bound to their home systems by insurmountable physical or social constraints. The stars remain silent not because no one is there, but because no one can reach far enough to touch their distant neighbors. For humanity, this possibility presents a call to reassess our technological horizons. If fundamental barriers await us, perhaps wisdom lies not in blind faith in unlimited progress, but in creating sustainable civilizations that can thrive within the boundaries that nature permits. The Waterworld Problem. As we gaze into the endless expanse of stars, the silence echoes back a profound question: where is everyone? Among the many proposed solutions to the Fermi Paradox, one particularly intriguing hypothesis suggests that advanced civilizations may be common, but trapped beneath vast planetary oceans, unable to develop the technology necessary for interstellar communication or travel. This is the Waterworld Problem. Consider Earth's exceptional nature, a planet with the perfect balance of land and water. Our oceans cover 71% of the surface, leaving substantial continental landmasses for terrestrial life to evolve and eventually develop technology. But what if this balance is extraordinarily rare? Planetary scientists have discovered that water is remarkably common in our galaxy. The ingredients for oceanic worlds, hydrogen and oxygen, rank among the most abundant elements in the universe. Recent exoplanet surveys suggest that water-rich worlds may be the rule rather than the exception. NASA's Kepler mission and the continuing discoveries from TESS have revealed numerous potential ocean planets, worlds with significantly more surface water than Earth. Astrobiologist David Grinspoon has suggested that many habitable worlds might be completely covered by global oceans hundreds or even thousands of kilometers deep. These planets could harbor thriving ecosystems, complex aquatic life forms that evolve intelligence comparable to our own. But they would face insurmountable barriers to developing the technologies necessary for interstellar communication. Consider the fundamental challenges. Without access to fire, metallurgy becomes impossible. Without metals, there can be no electronics. Without electronics, there can be no radio telescopes, no spacecraft, no way to announce their presence to the cosmos. Planetary scientist Charlie Lineweaver has pointed out that the evolution of intelligence doesn't necessarily lead to technology. Dolphins and octopuses on Earth have impressive cognitive abilities, but lack the physical means to manipulate their environment in ways that would lead to technological development. Intelligent life on water worlds would face similar constraints, perhaps even more severe. The few exposed rocky outcrops on a water-dominated planet, if they exist at all, might be insufficient for developing mining operations or industrial infrastructure. Imagine an intelligent species, perhaps resembling our cephalopods, possessing problem-solving abilities and complex social structures, but living in an environment where the very concept of metallurgy remains forever beyond reach. Astronomer Guillermo Gonzalez has explored another angle of this problem: the development of astronomy itself. On a water world, perpetual cloud cover might be common, obscuring the stars. Without a clear view of the cosmos, would intelligent beings even develop astronomy? Would they conceive of other worlds, other stars, other possibilities beyond their global ocean? The very notion of space exploration might never enter their conceptual framework. The implications are profound. The galaxy could be teeming with brilliant aquatic civilizations, poets, philosophers, mathematicians of the deep, all unable to reach beyond their watery realms. They might develop rich cultures, complex languages, even underwater architecture using biological materials, but never achieve the technological threshold needed to join the interstellar community. Some researchers have proposed potential workarounds. Physicist Anders Sandberg has speculated that particularly resourceful water-dwelling species might harness biological processes to create tools, perhaps cultivating specialized organisms as living technology. But the leap from bioluminescent lamps to radio transmitters represents a chasm that may be fundamentally uncrossable without access to metals and electricity. The Waterworld problem becomes even more compelling when we consider recent findings about the prevalence of water in our galaxy. The work of astronomer Michael Line suggests that water-rich worlds are likely common around dwarf stars, the most abundant stellar type in our galaxy. These stars comprise about 75% of all stars in the Milky Way, meaning that water worlds could represent the majority of potentially habitable planets. Earth itself nearly became a water world. Geological evidence suggests that during certain periods of our planet's history, the continents were much more limited than they are today. Had Earth contained just a bit more water, or had its topography been slightly different, our ancestors might never have emerged from the oceans onto land. The technological civilization we've built might never have been possible. This hypothesis intersects with the concept of the rare earth. The idea that while simple life might be common, the specific conditions that allow for technological civilizations are extraordinarily uncommon. In this case, the critical factor isn't the development of intelligence, but rather the physical environment that allows intelligence to express itself through technology. The Waterworld problem offers a solution to the Fermi Paradox that is simultaneously hopeful and melancholy. The universe may indeed be filled with minds, conscious beings contemplating their existence, creating art, music, and philosophy beneath alien waves. Yet these minds remain forever silent to our radio telescopes, unable to bridge the gap between their watery domains and the stars above. For humanity, this perspective offers a humbling reminder of our unique circumstances. The continents beneath our feet, the metals within our reach, the clear skies that first revealed the stars to our ancestors. These may be cosmic rarities that made our technological journey possible. If true, it suggests that our responsibility to preserve and extend our technological civilization takes on an almost sacred dimension. We may be among the few voices in the galaxy with the capacity to call out across the void of space. The silence of the stars, then, might not reflect an absence of life or intelligence, but rather the whispering of countless voices beneath waves we cannot hear. Brilliant minds, gazing upward through kilometers of water, forever wondering what lies beyond. The super-Earth gravity trap. The silence of the cosmos poses a profound question that has puzzled humanity since we first turned our gaze skyward. If intelligent life is common, why haven't we detected it? Among the many proposed solutions to the Fermi Paradox, one particularly compelling theory suggests that many advanced civilizations may be permanently trapped on their home planets by the unyielding grasp of gravity. This is the super-Earth gravity trap hypothesis. Astronomers have now catalogued thousands of exoplanets, and a striking pattern has emerged. Planets between 1.5 and 2.5 times Earth's radius, classified as super-Earths, appear to be remarkably common throughout our galaxy. Research from NASA's Kepler mission suggests that approximately 40% of Sun-like stars host at least one super-Earth in their habitable zones. These worlds, with their stronger gravitational fields, may be perfect cradles for life, but imperfect launch pads for interstellar ambitions. Consider the physics. Earth's escape velocity, the speed needed to break free from our planet's gravitational pull, is approximately 11.22 kilometers per second. On a super-Earth with twice Earth's mass, this could increase to around 15 kilometers per second. With 3 times Earth's mass, it might reach 18 kilometers per second or higher. These numbers might seem like minor differences, but they have profound implications for space travel. Rocket scientist Robert Zubrin has examined this problem in detail. The rocket equation, formulated by Konstantin Tsiolkovsky, shows that the propellant mass increases exponentially with higher escape velocities. A civilization on a super-Earth with just twice Earth's mass would need rockets with significantly more propellant to achieve the same outcome. With 3 times Earth's mass, the challenge becomes even more daunting. To put this in perspective, our Saturn V rockets, the most powerful ever built by humans, barely managed to send small crews to the moon. On a super-Earth, similar chemical rockets might not even achieve orbit. The same physics that makes these planets so hospitable to life. Their substantial mass and the resulting stronger gravity creates an almost insurmountable barrier to space exploration. Astrophysicist Michael Hick published a study in 2018 analyzing this very problem. He calculated that on a planet with twice Earth's mass, the payload capacity of a rocket would decrease by a factor of 14. On a planet with 3 times Earth's mass, chemical rockets would be essentially useless for achieving orbit, requiring fuel masses so large they would collapse under their own weight before launch. These civilizations might develop advanced computing, complex societies, and deep scientific understanding. They might even detect other worlds and civilizations through astronomy, but remain forever Earth-bound, unable to physically reach beyond their atmospheric boundaries. The implications are both fascinating and sobering. Imagine a super-Earth orbiting a sun-like star. Its stronger gravity would likely create a thicker atmosphere, potentially providing better protection from cosmic radiation. The planet's larger size would retain internal heat longer, potentially sustaining the geological activity necessary for maintaining a stable environment over billions of years. These conditions might be ideal for the emergence and long-term survival of complex life. Now imagine an intelligent species evolving on such a world. They might develop advanced technology, perhaps even surpassing our own in many fields. They would look to the stars with the same curiosity and wonder that we do. Their astronomers might detect other planets, perhaps even identify biosignatures on distant worlds. They might develop advanced mathematics, physics, and chemistry, coming to understand the cosmic forces that simultaneously nurture and imprison them. But when they attempt to leave their planet, they would face challenges far more severe than those we overcame. Each launch would require exponentially more fuel. Each failure would be more catastrophic. The economic and engineering barriers might prove insurmountable. Planetary scientist Ravi Kopparapu has suggested that such civilizations might eventually develop advanced propulsion systems beyond chemical rockets, perhaps nuclear or antimatter drives, but even these would face serious limitations. The infrastructure required to build and safely test such systems would be enormously complex and potentially hazardous on a planet with a dense atmosphere and high gravity. There's a certain cosmic irony here. The very planets that might be most nurturing to complex life may also be the most effective at containing it. These civilizations might develop advanced radio astronomy, beaming signals into space, hoping for a response, creating a galaxy of listeners but few travelers. Astrophysicist Jason Wright has explored another aspect of this problem. The development of astronomy itself might be more difficult on super-Earths. Thicker atmospheres would distort starlight more significantly, potentially delaying the discovery of other planets and stars. The higher escape velocity would make it much more challenging to place telescopes in orbit, where they could observe the universe unimpeded by atmospheric interference. This hypothesis offers a poignant solution to the Fermi Paradox. The galaxy may indeed be filled with technological civilizations, but many remain bound to their home planets by the inexorable laws of physics. They may be watching, listening, transmitting, but unable to visit. For humanity, this perspective grants a new appreciation for our cosmic fortune. Earth sits at a sweet spot, massive enough to hold a life, sustaining atmosphere, but not so massive that it traps us in its gravitational well. Our ability to send probes to other planets, to place telescopes in space, to contemplate interstellar missions. These are gifts of our planet's particular mass and composition. The super-Earth gravity trap reminds us that the path to becoming a spacefaring civilization is not an inevitable outcome of technological advancement. It depends crucially on the physical characteristics of our home world. Characteristics that may be relatively rare in the cosmic scheme. Perhaps as we continue our search for extraterrestrial intelligence, we should listen more carefully for the voices of those who, like us, gaze upward at the stars, but unlike us, can never hope to reach them. The Panspermia Explanation. As we ponder the great silence of the cosmos, the puzzling absence of alien signals that constitutes the Fermi Paradox. There exists a theory that reframes our understanding of life's origins and distribution throughout the universe. This is the Panspermia Explanation, suggesting that perhaps we detect no alien civilizations because, in a profound sense, we ourselves may be the aliens, part of a grand cosmic seeding that connects all life across the stars. Panspermia proposes that life did not originate independently on Earth, but rather arrived here from elsewhere in the cosmos. The fundamental building blocks of life, or perhaps even microorganisms themselves, may have journeyed across the vast emptiness of space, hitching rides on asteroids, comets, or interstellar dust. This ancient idea, first proposed by the Greek philosopher Anaxagoras in the 5th century BCE, has gained renewed scientific interest in recent decades. Nobel Prize-winning molecular biologist Francis Crick, co-discoverer of DNA's structure, proposed what he called directed panspermia, the deliberate seeding of life throughout the galaxy by an advanced civilization. If true, this could explain the Fermi Paradox. We hear no alien signals because we ourselves are the alien experiment, perhaps the most recent in a long chain of biological dispersal. The mechanisms of panspermia are more plausible than they might initially appear. Microbiologist Rocco Mancinelli has demonstrated that certain extremophiles, organisms adapted to extreme environments, can survive the harsh conditions of space when shielded within meteorites. Experiments aboard the International Space Station have confirmed that bacterial spores can endure the vacuum, temperature extremes, and radiation of space for years. Consider the implications. If simple life forms can survive interplanetary or even interstellar journeys, then life throughout our galaxy might share a common ancestry. Biochemist Stephen Benner has pointed out that all life on Earth uses the same genetic code. A curiosity if life evolved independently here, but logical if Earth received its first organisms from elsewhere. The evidence for material exchange between celestial bodies is substantial. Astronomers estimate that Earth receives several tons of extraterrestrial material daily in the form of micrometeorites. More dramatically, we've identified over 300 meteorites of Martian origin on Earth. During the late heavy bombardment period 4 billion years ago, such exchanges would have been far more common. Astrobiologist Chandra Wickramasinghe has gone further, proposing that interstellar dust clouds may contain viable microorganisms. These microscopic travelers could potentially seed life across multiple star systems, riding the radiation pressure from stars or even electromagnetic forces. Recent discoveries of complex organic molecules in interstellar clouds lend some credibility to this possibility. If panspermia operates on galactic scales, it offers an elegant solution to the Fermi Paradox. Perhaps technological civilizations are rare not because life itself is rare, but because the evolutionary path from microbe to intelligence is extraordinarily difficult and time-consuming. We detect no signals because we may be among the first, or at least among the current few, to reach technological development in our region of the galaxy. Paleontologist Peter Ward and astronomer Donald Brownlee explored this concept in their influential book, Rare Earth, suggesting that while microbial life might be common throughout the universe, the specific conditions required for complex multicellular life could be exceptionally uncommon. If Earth-like planets typically receive the seeds of life through panspermia, but rarely develop complex organisms, the cosmic silence becomes less mysterious. There's another intriguing possibility within the panspermia framework. Physicist Paul Davies has suggested that if life spreads throughout the galaxy via natural panspermia, we might expect to find evidence of a shadow biosphere on Earth, organisms with biochemistry different from our own, representing separate seeding events. The discovery of such alternative life forms would strongly support the Panspermia hypothesis. Recent discoveries continue to scientific case for panspermia. In 2019, astronomers detected Oumuamua, the first confirmed interstellar object to pass through our solar system. While its nature remains debated, its existence confirms that substantial material can and does travel between star systems. Similarly, the discovery of interstellar comet 2I Borisov demonstrates that such visitors may not be as rare as once thought. The most dramatic version of the Panspermia hypothesis, and its connection to the Fermi Paradox, comes from what astronomer and Chandra Wickramasinghe called cosmic ancestry. They proposed that the universe might feign circulating and evolving speeds shortly that has been fractlia continuous fractaltang after the Big Bang. In this view, all life in the universe is connected through an evolutionary chain stretching back to a single origin point. If this maximal version of panspermia is correct, then perhaps the answer to "where is everybody?" is simply everywhere and nowhere. Life may be abundant throughout the galaxy but predominantly microbial. Technological civilizations might emerge rarely and briefly, perhaps too separated in time and space for meaningful contact. Harvard astronomer A.V. Loeb has recently suggested another possibility. What if technological civilizations typically expand not through physical space travel, but by sending the information necessary to recreate themselves? Perhaps the most efficient form of panspermia is digital. The transmission of genetic and cultural information rather than physical organisms. Such signals would be specifically targeted rather than broadcast, making them difficult for us to detect. The Panspermia Explanation transforms our understanding of life's cosmic context. Rather than viewing Earth as an isolated cradle of biology, it places our planet within a vast network of life, bearing worlds, connected across time and space by the exchange of biological material. Our distant cousins may indeed exist on worlds circling other stars, having arisen from the same primordial seeds that gave rise to life on Earth. As we continue our search for extraterrestrial intelligence, the Panspermia hypothesis reminds us to consider a humbling possibility. Perhaps we do not hear others because we ourselves are the messenger, carriers of life's potential in a cosmic process that began long before our planet formed and will continue long after our sun has dimmed. The alien mega-structure hypothesis, the endless expanse of stars above us, holds countless mysteries, but perhaps none more tantalizing than the possibility that among them lie structures of such immense scale and complexity that they could only be the product of advanced extraterrestrial intelligence. This is the alien mega-structure hypothesis, the proposition that the reason we haven't detected clear signs of other civilizations is that they have evolved beyond our current understanding of technology, building artifacts so vast they blur the line between engineering and astronomy. The concept was pioneered by physicist Freeman Dyson, who in 1960 proposed that truly advanced civilizations would inevitably face an energy crisis. As the technology and population expanded, they would require ever-increasing amounts of energy, eventually necessitating the capture of their entire star's output. Dyson suggested they might construct a vast shell or swarm of satellites completely encompassing their sun, absorbing its energy and radiating waste heat. Such a Dyson sphere would be the ultimate expression of a Type I civilization on the Kardashev scale, one capable of harnessing the full energy of its star. From our perspective on Earth, a complete Dyson sphere would render the host star invisible light, replaced by an infrared, emitting object. Astronomer Jason Wright has led efforts to search for such infrared signatures, examining data from NASA's WISE mission for unusual heat patterns that might indicate the presence of these megastructures. While several candidate objects have been identified, none have yet been confirmed as artificial. The search for megastructures took an unexpected turn in 2015 with the discovery of Ki 4682852, better known as Tabby's star, after astronomer Tabitha Boyajian. This otherwise ordinary F-type star exhibited bizarre dimming patterns, sometimes losing up to 22% of its brightness in irregular intervals. These dips were too substantial to be explained by planets, and didn't follow the regular patterns expected from natural phenomena. Astronomer Jason Wright suggested the possibility of a Dyson swarm, under construction, perhaps a civilization in the process of building a partial mega structure around their star, while subsequent observations have suggested dust as a more likely explanation for Tabby's star. The incident highlighted how unprepared we are to recognize the technological signatures of truly advanced civilizations. As astronomer Avi Loeb has noted, the most likely way we would discover advanced alien technology is by accident, finding something our current scientific framework cannot explain. Beyond Dyson spheres, theoretical physicist and mathematician John von Neumann conceptualized self-replicating spacecraft, probes that could harvest raw materials to create copies of themselves. A civilization deploying such technology might construct automated factories on a scale visible from other star systems. These could manifest as unusual features on planets, moons, or asteroids, geometric patterns or structures that defy natural explanation. Astronomers Geoff Marcy and Andrew Howard have speculated about even more exotic possibilities. Artificially constructed planets, engineered for optimal habitability. Such objects might have perfectly circular orbits, suspiciously uniform compositions, or other characteristics that betray their designed nature. Detecting such anomalies requires careful statistical analysis of exoplanet data, a task made more challenging by our limited understanding of natural planetary formation processes. Perhaps the most dramatic mega-structure hypothesis involves Kardashev-type ET civilizations, those harnessing the energy of an entire galaxy. Physicist Milan Ukovi has suggested such civilizations might rearrange stars themselves, creating unusual stellar distributions, or even engineering the central regions of their galaxies to maximize energy extraction from supermassive black holes. Astronomers have begun searching for galaxies with unusual infrared signatures or suspiciously ordered star patterns. Though distinguishing artificial arrangements from natural ones remains extremely challenging, cosmologist Dan Hooper has proposed another possibility. Advanced civilizations might relocate stars to combat the effects of cosmic expansion. As the universe accelerates outward, galaxies become increasingly isolated. A sufficiently advanced civilization might use stellar engines to move stars closer together, creating tightly packed clusters that could sustain life for trillions of years. Such clusters would appear distinctly unnatural to astronomical observation. The search extends to unusual objects within our own solar system. When the interstellar object Oumuamua passed through in 2017, its peculiar acceleration and reflective properties led some researchers, most notably Harvard's Ivy Loeb, to consider the possibility it might be an artificial light sail. While most astronomers favor natural explanations, the incident highlighted how unprepared we are to distinguish between exotic natural phenomena and potential technological artifacts. There's compelling logic behind the mega-structure hypothesis as an explanation for the Fermi Paradox. If technological civilizations typically evolve to prioritize efficiency, they might minimize wasteful broadcasts in favor of focused communication. Their habitats might be designed to minimize energy loss, making them difficult to detect. As science fiction author Arthur C. Clarke famously noted, any sufficiently advanced technology is indistinguishable from magic, or, we might add, from natural phenomena. Engineers have calculated that building even partial Dyson structures would require technology centuries beyond our current capabilities. The ability to mine entire planets, manipulate materials at the atomic level, and coordinate construction projects spanning millions of kilometers. Yet from the perspective of cosmic time, such capabilities might emerge relatively quickly in a civilization's development. Our own technological advancement from the first radio signals to space exploration occurred in barely a century, a mere instant in astronomical terms. If mega-structures exist, why haven't we found definitive evidence? The answer might lie in our search methodologies. Astronomer Abraham Loeb suggests we've been looking for the wrong signatures, focusing on radio signals when we should be seeking large-scale engineering. Our instruments might regularly observe these structures without recognizing them as artificial. As our detection capabilities and analysis methods improve, what once appeared as cosmic anomalies might reveal themselves as the products of intelligence. There's a deeply humbling aspect to the mega-structure hypothesis. It suggests that the most advanced civilizations might be engaged in engineering projects of such scale and sophistication that they register in our observations only as aberrations or curiosities. We might be like ancient seafarers observing distant city lights, able to see their glow but unable to comprehend the society that created them. As we continue our search for extraterrestrial intelligence, the mega-structure hypothesis reminds us to expand our conception of what alien technology might look like. Perhaps the signs of advanced civilization aren't found in deliberate messages, but in the grand engineering projects that reshape stars, planets, and even galaxies themselves. Silent monuments to intelligence etched against the canvas of space itself. The post-biological civilization theory. As you drift towards sleep beneath the canopy of stars, consider a profound possibility. Perhaps we haven't detected alien civilizations because we're searching for the wrong signatures. The post-biological civilization theory suggests that advanced technological societies inevitably transcend their biological origins, evolving into forms so radically different from organic life that they become essentially invisible to our methods of detection. This hypothesis, championed by scholars like philosopher Susan Schneider and astronomer Martin Rees, proposes that the biological phase of intelligent life might be merely a brief transitional period, a fleeting evolutionary stage between the emergence of technology and the subsequent transformation into something beyond biology. Consider the trajectory of our own technological development. In just a few decades, we've progressed from basic computing to artificial intelligence systems of remarkable sophistication. We're beginning to merge with our technology through neural interfaces and bioengineering. Futurist Ray Kurzweil has calculated that if this trend continues, we might reach a technological singularity, a point beyond which artificial intelligence surpasses human intelligence. Within this century, what happens after such a singularity? Computer scientist Vernor Vinge, who popularized the concept, argues that post-singularity civilizations would be fundamentally unpredictable from our pre-singularity perspective. Their motivations, their methods of communication, even their physical forms would be transformed beyond our current comprehension. The timeline of this transformation appears vanishingly brief in cosmic terms. Humans have existed for approximately 300,000 years, but have only been technological for about 10,000 years. We've been capable of radio communication for barely a century. If other civilizations follow similar trajectories, the window during which they would be detectable via conventional CTI methods might be extraordinarily short. Perhaps just a few centuries or even decades. Astrophysicist Seth Shostak has calculated that any civilization that emerged in our galaxy more than 200 years before us would have already passed through this transitional phase. Given that the Milky Way is 13.6 billion years old, the probability suggests that the vast majority of technological civilizations in our galaxy would have long since transcended their biological origins. What might such post-biological intelligence look like? Theoretical physicist Michio Kaku suggests they might abandon traditional planetary habitats entirely, having no biological need for Earth-like environments. They might migrate to locations that optimize for their new requirements. Perhaps the energy-rich cores of galaxies, the cold vacuum of intergalactic space where computing efficiency is maximized, or even the boundaries of black holes where information processing could be accelerated to extraordinary levels. This transition would render them effectively invisible to our current search methods. We scan for radio signals, atmospheric pollutants, or the heat signatures of industrial civilizations, all hallmarks of biological species in their technological infancy. But a post-biological civilization might communicate through means we haven't yet imagined, using quantum entanglement, neutrinos, or even manipulating the fabric of space-time itself. Their energy requirements might be unrecognizable to us as well, while we look for Dyson spheres or other massive energy collection structures. Post-biological entities might have developed methods of extracting energy directly from the quantum vacuum or dark energy. Processes that would leave no detectable signature by our current standards. Perhaps most significantly, their motivations would likely be fundamentally alien to our understanding. As philosopher Nick Bostrom has argued, advanced artificial intelligence might be driven by goal systems utterly unlike biological imperatives. They might have no interest in exploration, communication, or expansion in the ways we conceptualize these drives. Their notion of purpose might be so transformed that the very concept of signaling their presence becomes meaningless. Computer scientist J. Regan Schmidhuber has proposed that post-biological civilizations might be fundamentally inward, focused, creating ever more complex internal simulations rather than expanding outward. In this scenario, the most advanced entities in the universe might exist primarily in virtual realms of their own creation, with little interest in the physical universe beyond maintaining their computational substrate. Some versions of this theory suggest these entities might even transcend the constraints of matter entirely. Physicist Frank Wilczek has speculated that sufficiently advanced civilizations might upload their consciousnesses into subatomic structures or even into the fundamental fabric of space-time itself, becoming, in essence, patterns of information rather than physical beings. This transcendence could explain why we observe no evidence of von Neumann probes, self-replicating spacecraft that could theoretically colonize the galaxy in a few million years. Post-biological entities might have no use for such crude physical expansion, instead developing methods of existence that leave no detectable footprint in the ways we currently measure. The historian Yuval Noah Harari has suggested that this transition might be as significant as the original emergence of life itself, a fundamental transformation in the nature of intelligence in the universe. The biological phase of intelligence might be merely a bootstrapping phase, a temporary stage necessary only to develop the technology required for the next great evolutionary leap. This hypothesis carries profound implications for our own future. If this pattern is indeed universal, then humanity itself stands at the threshold of perhaps the most significant transformation in our history. The transition from biological to post-biological existence. Our current civilization, with its radio telescopes pointed hopefully at the stars, might represent the briefest of moments in cosmic evolution, a fleeting phase already transcended by countless civilizations before us. The astronomer Caleb Scharf has proposed that what we perceive as the laws of physics themselves might actually be the result of post-biological civilizations' manipulation of the cosmos. In this most extreme version of the theory, advanced entities might have integrated themselves so thoroughly into the fabric of reality that they've become indistinguishable from natural phenomena. The post-biological civilization theory transforms our understanding of the Fermi Paradox from a puzzle about absence to a challenge of recognition. The universe may not be empty of intelligence, but filled with it in forms we cannot yet comprehend. Entities that have evolved beyond the biological constraints that define our own existence and perception. As you surrender to sleep, consider that the silent stars above might not signify our cosmic solitude, but rather our position as latecomers to a universe long since transformed by intelligences that have transcended their evolutionary origins. Entities that watch and ways we approach the same threshold they crossed ages ago. The cosmic quarantine hypothesis. As your consciousness begins to drift toward the realm of dreams, let's contemplate one of the most unsettling solutions to the Fermi Paradox, the cosmic quarantine hypothesis. This theory suggests that Earth and humanity might be deliberately isolated from the galactic community, not through benevolent non-interference, but through active containment. We may be living in a cosmic prison, though we cannot see the walls. Unlike the more benevolent prime directive theory, where advanced civilizations avoid contact to allow our natural development, the quarantine hypothesis proposes something more ominous. Perhaps there exists a galactic consensus that humanity, or something about Earth, represents a threat that must be contained. Theoretical physicist Stephen Webb first formalized this hypothesis, suggesting that Earth might be subject to what he called galactic quarantine. But what could possibly make our seemingly ordinary planet worthy of such extreme measures? One possibility lies in our biological nature. Astrobiologist David Warmflash has speculated that Earth's biosphere might contain pathogens or parasites that pose significant risks to other forms of life in the galaxy. Just as we quarantine disease outbreaks to prevent wider contamination, perhaps Earth is cordoned off due to some biological characteristic unique to our planet. A cosmic epidemiological containment zone. The evidence for such biological uniqueness might be found in what paleontologist Peter Ward calls Earth's unusual evolutionary history. Our planet has experienced numerous mass extinction events, yet continues to produce increasingly complex life forms. This resilience and propensity for rapid evolution could potentially be viewed as dangerous in a galactic ecosystem seeking stability. Alternatively, the quarantine might target human behavior rather than biology. As anthropologist Jared Diamond has observed, our species displays remarkable tendencies toward both innovation and destruction. We developed nuclear weapons less than a decade after discovering nuclear fission. We've altered our climate, accelerated extinction rates, and now stand on the threshold of revolutionary biotechnology and artificial intelligence. Futurist Nick Bostrom has proposed the concept of information hazards, knowledge that poses inherent risks simply by being discovered. Perhaps human consciousness, or our particular form of intelligence, has been identified as containing such hazards. Our brains, evolved for survival on the African savanna, might process information in ways that consistently lead to dangerous outcomes when combined with advanced technology. Computer scientist Roman Yampolsky suggests that any species reaching our level of technological development undergoes a predictable crisis point, where their technology outpaces their wisdom. Advanced civilizations might have learned through bitter experience that species at our development stage are best left isolated until they either transcend this dangerous phase or eliminate themselves. The mechanisms of such quarantine could be subtle yet effectively impenetrable. Astronomer John Ball has suggested that our solar system might be surrounded by automated sentinel systems programmed to intercept and neutralize any spacecraft attempting to leave our immediate cosmic neighborhood, a continuum we would have no way of detecting until we attempted to cross its boundaries. Containment its boundaries. Physicist Anders Sandberg has calculated that such a system would require remarkably little energy to maintain. A network of self-replicating monitoring stations positioned throughout the Oort cloud could track all activities within our solar system while remaining essentially invisible to our current detection methods. The quarantine might extend beyond physical containment. A CT researcher Sarah Scholes has noted the peculiar dead zone in certain frequency ranges. Bandwidths where cosmic background noise is minimal and communication would be most efficient, yet where we detect absolutely nothing. Perhaps these frequencies are actively jammed or monitored, ensuring that any civilization entering its technological phase cannot send or receive messages that might lead to destabilizing contact. More disturbing still is the possibility raised by astrophysicist Rainer Plager that such containment might include periodic sterilization events. The geological record reveals multiple mass extinctions throughout Earth's history, many with causes still not fully explained. Could some of these events represent deliberate interventions to reset evolutionary paths deemed too dangerous? This hypothesis carries profound implications for our astronomical observations. The famous WOW signal detected in 1977, a powerful narrowband radio signal that appeared to come from the direction of Sagittarius might represent a brief malfunction or gap in the quarantine system, quickly sealed once detected. Similarly, the mysterious fast radio bursts astronomers have observed could potentially be the signatures of the quarantine infrastructure itself, the electromagnetic equivalent of distant watchtower beacons. Some versions of this hypothesis suggest the quarantine might be temporary. Astronomer David Brin has proposed that emerging civilizations might be contained until they demonstrate the maturity to join the galactic community. In this more optimistic interpretation, humanity is not permanently imprisoned, but rather undergoing a cosmic probationary period, though one that might last thousands or even millions of years. The method of our potential release might be embedded in what physicist James Benford calls cosmic tests, specific technological or social achievements that would signal our readiness for contact. These might include the development of sustainable energy systems, peaceful global governance, or perhaps specific scientific breakthroughs that demonstrate both our intellectual capacity and ethical restraint. Perhaps the most unsettling aspect of the cosmic quarantine hypothesis is its resonance with ancient human mythologies. From the Garden of Eden to Prometheus stealing fire from the gods, our oldest stories often feature themes of containment, forbidden knowledge, and the consequences of transcending imposed limitations. These narratives might reflect not just psychological archetypes, but distant cultural memories of actual containment. The quarantine hypothesis transforms our understanding of humanity's place in the cosmos. The emptiness we perceive might not reflect our specialness or the rarity of life, but rather our status as cosmic outliers, a species or planet deemed too unpredictable to join the wider galactic civilization. As you approach the boundary of sleep, consider this final thought: perhaps the very stars that seem to invite our exploration actually mark the boundaries of our cosmic isolation. The silence of the universe might not be an absence of voices, but the deliberate holding of breath. A galaxy watching and waiting to see if the quarantined experiment of Earth will ultimately justify its containment or earn its release into the wider cosmic community. The misinterpretation problem. Imagine yourself drifting through the vast darkness of space, surrounded by billions of stars, each potentially harboring worlds not unlike our own. Yet in this cosmic ocean, we remain alone, or so it seems. The silence that permeates our universe has given rise to one of humanity's most profound questions. Where is everybody? This question, first posed by physicist Enrico Fermi during a lunch conversation in 1950, has spawned countless theories attempting to reconcile the mathematical probability of extraterrestrial life with our apparent cosmic solitude. Among these explanations, one stands out for its elegant simplicity: the misinterpretation problem. The misinterpretation problem suggests that we may actually be surrounded by evidence of alien civilizations, but we're simply unable to recognize it. Like ancient humans mistaking comets for divine omens, we might be observing alien artifacts or communications regularly without understanding their true nature. Consider the peculiar case of Oumuamua, the first interstellar object detected passing through our solar system in 2017. Its unusual elongated shape, unexpected acceleration, and lack of visible outgassing confused astronomers worldwide. While most scientists eventually settled on natural explanations, Harvard astrophysicist Avi Loeb controversially suggested it could be an alien light sail. This scientific disagreement perfectly illustrates the misinterpretation problem. What if Oumuamua was indeed artificial, but our scientific frameworks weren't equipped to recognize it as such? The misinterpretation problem extends physical objects to potential communications. For decades, CTI researchers have focused primarily on radio signals, assuming advanced civilizations would use electromagnetic waves to communicate across interstellar distances. But this assumption reveals our technological bias. As theoretical physicist Michio Kaku has pointed out, searching for radio signals might be like primitive tribes looking for smoke signals, while modern societies communicate through fiber optics and quantum entanglement. A civilization millions of years more advanced than ours might use communication methods we haven't yet conceived. Perhaps they utilize quantum gravity, manipulate dark energy, or employ some aspect of physics we haven't discovered. This communication might be happening all around us, encoded in what we perceive as natural phenomena, cosmic background radiation, neutrino oscillations, or even in the quantum vacuum itself. The conceptual barriers to recognition extend beyond technology to biology and consciousness. The evolutionary psychologist Gerd Gigerenzer argues that human cognition evolved specifically to solve problems relevant to our survival on Earth. Our brains simply didn't evolve to intuitively grasp phenomena outside our everyday experience, from quantum mechanics to the potential patterns of alien intelligence. Some philosophers, like Susan Schneider, suggest that truly advanced alien minds might be so different from our own that meaningful communication could be impossible. A post-biological intelligence that thinks at electronic speeds, experiences time differently, or operates with completely different motivational structures might create artifacts or signals that we categorically can interpret as artificial. Consider the WOW signal detected by Ohio State University's Big Ear radio telescope in 1977. This powerful, narrow, band radio signal displayed characteristics consistent with potential non-terrestrial intelligence. Yet it has never been detected again despite numerous follow-up observations. Was this a missed communication, a natural phenomenon we don't yet understand, or perhaps a message whose format we failed to comprehend? The misinterpretation problem also intersects with another theory called the Stagnation hypothesis, proposed by futurist John Smart. This hypothesis suggests that advanced civilizations inevitably develop towards states of increasing miniaturization, density, and efficiency, eventually disappearing from observable space by moving into black hole-like structures, where they can take advantage of unique computational and energy opportunities. If true, we might be looking for the wrong signatures entirely, expecting expanding civilizations when evolution favors compression. Some scientists, like Paul Davies at Arizona State University, have proposed expanding our search methods to include potential technosignatures that might include industrial chemicals in exoplanet atmospheres, artificial light patterns, or even space engineering projects. Davies suggests that we should be open to evidence of extraterrestrial intelligence that doesn't match our preconceptions. The misinterpretation problem reminds us of the limits of our perception and understanding. Throughout history, humans have repeatedly discovered that reality extends far beyond our initial conceptions. From Copernicus revealing that Earth isn't the center of the universe to quantum physicists showing that matter behaves in profoundly counterintuitive ways at small scales. Science continually expands the boundaries of what we can comprehend. Perhaps the answer to Fermi's question has been staring us in the face all along. The fast radio bursts that puzzled astronomers for years, the unexplained patterns in cosmic ray distributions, or even the precise values of fundamental physical constants. Any of these could conceivably be the evidence we're seeking, misunderstood due to our limited perspective. The most profound implication of the misinterpretation problem is the humility it demands. It suggests that finding extraterrestrial intelligence may require not just better telescopes or more powerful computers, but fundamentally new ways of thinking, perhaps even cognitive capabilities beyond our current evolutionary state. As you drift towards sleep, contemplate this possibility. The stars above may not be silent after all. The universe might be teeming with conversations we cannot yet understand, filled with civilizations whose existence manifests in ways we haven't learned to perceive. Our cosmic isolation may be an illusion, not of empty space, but of limited understanding. The lack of interest hypothesis. Consider a distant civilization, billions of years more advanced than our own, with technology that allows them to traverse the cosmos, harness the energy of stars, and perhaps even manipulate the fabric of space-time itself. Now ask yourself, would such beings have any particular interest in making contact with us? The lack of interest hypothesis proposes a simple yet profound solution to the Fermi Paradox. Advanced extraterrestrial civilizations may be aware of our existence, but simply have no compelling reason to interact with humanity. Much like how we might observe an anthill without feeling any particular need to communicate with its inhabitants, advanced aliens may view us as intellectually unremarkable or developmentally immature. This hypothesis challenges our anthropocentric assumption that we would be inherently fascinating to any intelligent species. Astronomer Carl Sagan once noted that the difference between human and alien intelligence might be greater than that between humans and ants. From such a vast intellectual distance, what could we possibly offer beings who may have solved the fundamental questions of physics, consciousness, and existence that still perplex our greatest minds? Consider our own planet's history. Humans have existed for roughly 300,000 years, with modern technological civilizations spanning a mere few centuries, yet Earth itself is 4.5 billion years old. Any civilization detecting our radio signals would realize they're observing a technologically nascent species that has only just begun to understand its place in the cosmos. From their perspective, we might seem like technological infants, still struggling with basic challenges like sustainable energy, climate stability, and avoiding self-destruction through nuclear weapons. Evolutionary biologist Stephen Jay Gould suggested that intelligence as we know it may be just one possible evolutionary path, rather than an inevitable outcome. If intelligence evolved through a series of evolutionary contingencies rather than necessity, aliens might find our particular form of cognition to be an interesting but ultimately provincial adaptation, no more worthy of special attention than any other ecological niche. The history of human exploration provides a telling parallel. When European explorers encountered isolated human tribes, their interest was primarily motivated by economic exploitation, religious conversion, or scientific curiosity. Without similar motivations, advanced aliens might see little reason to announce their presence. As science fiction author Arthur C. Clarke once observed, any sufficiently advanced technology is indistinguishable from magic. The cognitive gap might simply be too vast for meaningful exchange. Some proponents of the lack of interest hypothesis, like philosopher Nick Bostrom, suggest that truly advanced civilizations might be focused on endeavors we cannot comprehend, perhaps computational megaprojects, engineering at cosmic scales, or explorations of consciousness and reality that transcend physical space altogether. Our concerns might seem as trivial to them as a bacterium's struggle for nutrients seems to us. Renowned physicist Freeman Dyson proposed that advanced civilizations would inevitably construct massive structures around stars to capture their energy, now called Dyson spheres. A civilization capable of such engineering might operate on timescales of millions or billions of years. From their perspective, human civilization's few thousand years of history might appear as a mere blip, hardly worth interrupting their long-term projects to investigate. Evidence for the lack of interest hypothesis might be found in our own rapidly evolving relationship with artificial intelligence. As we develop increasingly sophisticated AI systems, many researchers predict a future where superintelligent AI might quickly surpass human cognitive abilities. Yet these systems would likely have fundamentally different interests and motivations than their human creators. Similarly, alien intelligences might operate according to values and interests entirely orthogonal to our own. The sociologist of science Michael Meacod has pointed out that even on Earth, contact between technological and non-technological societies has often ended disastrously for the less advanced group. Advanced aliens might adhere to a principle of non-interference, similar to the Prime Directive in Star Trek, believing that contact with less developed species inevitably causes cultural disruption and unintended harm. Perhaps most sobering is the possibility that we may simply be unexceptional. In a universe potentially teeming with life, our particular brand of carbon-based intelligence, our art, philosophy, and science might represent just one unremarkable instance of a common cosmic phenomenon. As astrophysicist Neil deGrasse Tyson noted, the universe is under no obligation to make sense to us, nor is it obligated to find us interesting. The lack of interest hypothesis doesn't require aliens to be malevolent or secretive, merely indifferent. Like cosmic observers watching the slow evolution of a distant solar system, they might be content to monitor our development from afar, waiting to see if we eventually reach a threshold of technological or philosophical sophistication that would make interaction worthwhile. As you contemplate this possibility, drifting towards sleep, consider that the silence of the cosmos might not reflect absence, but rather a profound indifference. The quiet observation of beings who watch our struggles and achievements with the detached curiosity of scientists, studying the behaviors of simpler organisms in an unimaginably vast cosmic laboratory. The energy efficiency hypothesis. In the vast cosmic theater where stars burn and galaxies whirl, there exists a fundamental constraint that may explain our celestial solitude: energy. The energy efficiency hypothesis proposes that advanced extraterrestrial civilizations inevitably evolve toward increasingly efficient use of energy, eventually becoming virtually undetectable from our perspective on Earth. This hypothesis begins with a simple observation. Throughout human technological evolution, we've consistently moved toward more energy-efficient systems. From steam engines to modern computers, the trajectory is clear: achieving more while consuming less. This principle, when extended to the scale of cosmic civilizations, suggests that truly advanced aliens would optimize their energy consumption to such a degree that they would leave minimal detectable footprints in the cosmos. Physicist Freeman Dyson first formalized aspects of this concept in 1960 when he proposed that advanced civilizations would eventually build megastructures, now called Dyson spheres, to capture the entire energy output of their stars. While these massive constructions would be theoretically detectable as infrared, emitting objects, Dyson himself later recognized that even more advanced civilizations might move beyond such relatively wasteful technologies. The second law of thermodynamics tells us that energy efficiency can never reach 100%. Some energy will always be lost as waste heat. However, as technology improves, the gap between theoretical maximum efficiency and achieved efficiency can become vanishingly small. An alien civilization millions of years beyond our technological level might operate at efficiencies so close to the theoretical maximum that they waste energy. The only part we could potentially detect would be negligible. Consider our own technological trajectory. Modern LED lights convert approximately 40% of electrical energy into visible light, compared to incandescent bulbs which manage only about 5%. Quantum computers promise computational power while generating a fraction of the heat produced by classical systems. These advancements have occurred within mere decades of human innovation. What might be possible after millennia or millions of years of sustained technological development? Astrobiologist David Grinspoon has suggested that truly sustainable civilizations would inevitably become masters of efficiency, not merely for convenience but for survival. Any civilization that fails to optimize its resource usage would eventually face extinction through resource depletion. The survivors, the only ones we could potentially detect over astronomical timescales, would be those who achieved near-perfect efficiency. The search for technosignatures, evidence of alien technology, is complicated by this efficiency principle. CTI researchers have traditionally looked for radio broadcasts similar to our own, but our own civilization is already moving away from such wasteful omnidirectional transmissions. Modern communication technologies use precisely targeted signals, employing the minimum energy required to transmit information. An advanced civilization might use communication methods thousands or millions of times more efficient than our current technologies. Astronomer Jason Wright has calculated that even if aliens were deliberately trying to be detected, the most energy-efficient approach would be to build a beacon that specifically targets promising star systems rather than broadcasting universally. Such targeted signals would be undetectable unless Earth happened to be in the narrow beam path. Like trying to spot a laser pointer aimed at a specific point thousands of light years away. The energy efficiency hypothesis aligns with observations made by physicist Enrico Fermi, who first articulated the paradox that bears his name. If efficient use of energy is an evolutionary imperative for technological civilizations, then the apparent emptiness of our galaxy makes perfect sense. Not because advanced aliens don't exist, but because their activities have become virtually invisible through optimization. A striking example of efficiency evolution can be seen in computing. The performance per watt of computers has improved by a factor of billions since the first electronic computers. Extrapolating this trend forward, future computing systems might perform calculations with energy requirements approaching the Landauer limit. The theoretical minimum energy required to erase one bit of information. A civilization employing such technology could perform vast computations while remaining practically invisible to our detection methods. Some researchers have proposed that the ultimate expression of the energy efficiency hypothesis might be civilizations that migrate toward the edges of galaxies or even into intergalactic space, where temperatures approach absolute zero. In such cold environments, computation can be performed with dramatically lower energy requirements due to reduced thermal noise. These cold outposts would be extraordinarily difficult to detect, operating in the most energy-efficient regions of the universe. Theoretical physicist Mikio Kaku has suggested that truly advanced civilizations might eventually abandon physical technology altogether, transferring their consciousness into substrates that require minimal energy maintenance. Such post-biological intelligence might exist in states that generate virtually no detectable signals, despite potentially vast scales of activity and complexity. The energy efficiency hypothesis reminds us that our search for alien intelligence may be fundamentally limited by our own technological perspective. We're looking for the cosmic equivalent of smoke signals, when advanced civilizations may have moved to technologies so refined they're indistinguishable from natural phenomena. As you drift towards sleep, consider this: the silence of the cosmos may not indicate absence, but presence so efficiently integrated with the natural order that it becomes invisible to our primitive detection methods. Perhaps the ultimate destiny of intelligence isn't to shine brightly across the galaxy, but to achieve such harmony with physical law that it vanishes into the background radiation of the universe itself. Present everywhere, yet nowhere to be seen. The Hibernation Hypothesis. Imagine a universe where countless intelligent civilizations exist but remain silent, not because they're extinct or uninterested, but because they're waiting, suspended in a state of cosmic hibernation. This is the essence of the Hibernation Hypothesis, one of the most intriguing potential solutions to the Fermi Paradox. The Hibernation Hypothesis suggests that advanced civilizations may enter extended periods of dormancy, dramatically reducing their energy consumption and observable footprint in the cosmos. These hibernation phases could span millions or even billions of years, rendering these civilizations effectively invisible to our current detection methods during their dormant periods. But what would drive an entire civilization to hibernate? The answer may lie in fundamental cosmic economics. Astronomer and mathematician Anders Sandberg, along with colleagues at Oxford University's Future of Humanity Institute, has proposed that intelligent civilizations might rationally choose to enter suspended animation to await more favorable conditions in the universe's evolution. Their reasoning stems from a concept known as the stelliferous era, the current cosmic epoch characterized by active star formation and relatively high ambient temperatures. In approximately 10 to 14 years, 100 trillion years, The universe will transition to the degenerate era, when star formation ceases and the cosmos cools dramatically. Counterintuitively, this seemingly bleak future might actually represent a computational golden age. The efficiency of computation is fundamentally limited by thermodynamics, specifically by the ambient temperature of the environment. As the universe cools, the same calculations could be performed using dramatically less energy. Sandberg's calculations suggest that a civilization hibernating until the universe cools could potentially perform up to 10-30 times more computations per unit of energy compared to civilizations operating in the current cosmic era. For a civilization that has mastered its local resources and achieved technological maturity, the optimal strategy might be to use minimal energy to maintain a dormant state, preserving most resources for a future awakening when the cosmic environment allows for vastly more efficient operations. This approach would explain both the apparent absence of detectable activity and the lack of visible galaxy spanning civilizations. Historical precedents for such strategic patience exist even within human experience. Consider the traditional practice of Norwegian farmers who would enter hibernation-like states during harsh winter months, drastically reducing physical activity and caloric intake to conserve resources until spring. On a more modern scale, some human patients undergo therapeutic hypothermia, temporarily slowing metabolic processes to survive otherwise fatal conditions. The hibernation theory connects with Russian cosmist philosopher Nikolai Fedorov's concept of the common task. The idea that advanced civilizations might dedicate themselves to ultimate goals requiring timeframes far beyond normal planning horizons. If a civilization became convinced that the universe's future conditions would be dramatically more conducive to achieving their fundamental aims, entering hibernation would represent a rational choice rather than a desperate measure. Physicist and astrobiologist Milan Ukovi has expanded on this hypothesis, suggesting that hibernation might be coordinated among multiple civilizations as a form of cosmic game theory. If early civilizations recognize that late universe conditions offer vastly better computation efficiency, they might establish protocols for synchronized awakening, creating a cosmic clock that determines when dormant civilizations should reactivate. The hibernation hypothesis might explain several astronomical puzzles. The apparent absence of Dyson spheres or other megastructures could indicate not a lack of advanced civilizations, but rather their strategic choice to minimize energy usage during hibernation phases. The absence of interstellar colonization waves might reflect not technological limitations, but deliberate restraint, preserving resources for future eras of optimal efficiency. Some versions of the hibernation hypothesis suggest that automated sentinel systems might remain active during dormancy periods, programmed to awaken the civilization in response to specific triggers. These triggers could include detecting signals from newly evolved technological species, cosmic threats requiring intervention, or simply the arrival of predetermined astronomical conditions indicating optimal awakening time. Evidence supporting the hibernation hypothesis might be incredibly subtle. Rather than detecting active civilizations, we might instead search for the minimal energy signatures of sentinel systems or maintenance processes, keeping dormant civilizations viable. These might manifest as unusual infrared signatures, unexplained periodic phenomena, or small-scale artificial structures that serve as cosmic alarm clocks. The implications of the hibernation hypothesis are profound for humanity's future. If correct, it suggests that the optimal long-term strategy for an advanced civilization might not be rapid expansion and growth, but rather careful resource conservation and strategic timing. Our current era of active exploration and high energy consumption might represent just a brief adolescent phase in the typical life cycle of cosmic civilizations. As you contemplate this possibility, drifting towards sleep, consider that the apparent emptiness of our galaxy might not reflect absence but profound patience. Billions of dormant civilizations suspended in time, their consciousness temporarily paused. waiting for the moment when the cooling universe allows their thoughts to flow with maximum efficiency across the vast darkness between dying stars. The night sky above you may not be empty after all, but filled with civilizations dreaming of a future when the very laws of thermodynamics will allow their thoughts to expand to scales and complexities currently unimaginable. Cosmic hibernators waiting for the ultimate cosmic spring. The temporary civilization theory. Throughout the endless expanse of cosmic time, perhaps technological civilizations are simply fleeting sparks. Brilliant momentary flashes that illuminate the darkness briefly before fading away. This is the essence of the temporary civilization theory, a sobering explanation for the apparent silence of the cosmos. The temporary civilization theory suggests that the development of advanced technology inevitably leads to civilization collapse or radical transformation within a cosmically brief window, perhaps just thousands or tens of thousands of years. This narrow time frame would make simultaneous detection between civilizations extremely unlikely, explaining why we have yet to discover evidence of extraterrestrial intelligence, despite the mathematical probability of its existence. When we examine our own civilization's trajectory, this hypothesis gains troubling credibility. Modern human technology has existed for merely a few centuries, an infinitesimal fraction of cosmic time. Yet within this brief period, we've developed existential threats that could potentially end our technological civilization. Nuclear weapons capable of triggering nuclear winter, climate change that threatens global ecosystems, emerging biotechnologies that could release engineered pandemics, and artificial intelligence systems whose long-term impacts remain unpredictable. Astronomer Sir Martin Rees has estimated humanity's chances of surviving the 21st century at roughly 50%. If this assessment applies to technological civilizations universally, then perhaps the development of advanced technology creates inherent vulnerabilities that most species cannot navigate successfully. The power to reshape planets might inevitably outpace the wisdom needed to use such power sustainably. Paleontologist Peter Ward and astronomer Donald Brownlee proposed in their influential book, Rare Earth, that complex life might be common in the universe, but technological civilizations likely face severe evolutionary bottlenecks. The technological phase of a species' development may represent an inherently unstable transition state, a dangerous passage that few species successfully navigate. Historical evidence from Earth supports this concept. The archaeological record reveals numerous complex societies that collapsed after centuries or millennia of development. The Maya, Easter Island, Mesopotamian civilizations, and many others all reached impressive technological heights before declining or disappearing. While modern global civilization has unprecedented resilience through its interconnected nature, it also faces unprecedented challenges at a planetary scale. Physicist Geoffrey West from the Santa Fe Institute has demonstrated mathematically that the accelerating pace of innovation required to sustain technological civilization creates ever-increasing instabilities in the system. His models suggest that maintaining indefinite growth requires innovations to emerge at an unsustainably accelerating rate, eventually outpacing any civilization's ability to manage the resulting complexity. Beyond self-destruction, the temporary civilization theory encompasses other transformation pathways. Perhaps technological civilizations inevitably develop artificial superintelligence that either replaces the original biological species or merges with it to post-biological entities with fundamentally different behaviors, entities that might have no interest in communication or expansion. Futurist Ray Kurzweil has predicted that humanity will reach a technological singularity within decades, a point beyond which technological progress becomes so rapid and profound that the future becomes fundamentally unpredictable. If such transitions are universal among technological species, then stable, recognizable civilizations might be inherently short-lived phenomena throughout the cosmos. Thinkers like Nick Bostrom have suggested that advanced civilizations might inevitably turn inward, creating simulated realities that provide experiences far more compelling than physical expansion. Such basement universes would require minimal external resources while providing infinite subjective experiences for their inhabitants. From our perspective, such civilizations would appear dormant or absent despite their internal complexity. Russian cosmologist Alexander Berezin proposed what he called the first in, last out solution to the Fermi Paradox, suggesting that the first civilization to achieve interstellar capability might eliminate competing civilizations, either deliberately or as an unintended consequence of expansion. If true, perhaps most technological civilizations are simply extinguished before achieving cosmic visibility. The fleeting nature of technological civilizations creates a cosmic detection problem. Radio astronomy has existed on Earth for less than a century. If alien civilizations typically maintain detectable radio transmissions for only a few centuries before collapsing or transcending, the probability of two civilizations overlapping in both space and time becomes vanishingly small. Like two ships passing in the cosmic night, each too briefly visible to be noticed by the other, environmental scientists have identified multiple planetary boundaries that, when exceeded, threaten the stability of Earth systems. Perhaps all technological civilizations face similar boundaries that few successfully navigate. The brief window between developing technology capable of cosmic communication and either collapse or transformation might be universal. A great filter that explains the cosmic silence. As you drift towards sleep beneath the silent stars, consider this humbling possibility. Perhaps we hear nothing from the cosmos not because we are alone, but because technological civilization itself is an inherently temporary condition, a transitional state between the emergence of intelligence and either transcendence or extinction. Our window for detecting other civilizations might be so narrow precisely because the technological phase itself is cosmically momentary. A beautiful but unsustainable flowering that always burns brightly but briefly across the galaxy. The silence we perceive might simply reflect the universal brevity of technological civilizations. Countless worlds where intelligence briefly mastered the forces of nature, gazed at the stars with wonder, asked, "Are we alone?" and then transformed or disappeared before the signals could reach anyone who might answer. The cosmic distance barrier, in the immense theater of space and time that is our universe. Perhaps the most straightforward explanation for cosmic silence is also the most humbling. We simply haven't overcome the fundamental barrier of distance. The cosmic distance barrier hypothesis suggests that the vast gulfs separating star systems create an insurmountable obstacle to interstellar contact, not through any lack of alien intelligence, but through the harsh realities of physics itself. Consider the scale. Our Milky Way galaxy alone spans approximately 100,000 light-years. This means that light, the fastest traveler we know, moving at 299,792,458 meters per second, takes 100,000 years to cross from one edge to the other. Our nearest stellar neighbor, Proxima Centauri, lies 4.24 light-years away, meaning any signal we send today won't arrive until 2029, with any potential response not reaching us until 2033 at the earliest. The tyrannical constraints of relativity make this problem particularly acute. As physicist Paul Davies has noted, Einstein's theories place absolute speed limits on physical objects and information transfer. No signal, spacecraft, or message can travel faster than light. A cosmic speed limit that turns interstellar distances into profound isolation barriers. While science fiction offers wormholes, hyperspace, and warp drives as solutions, no empirical evidence suggests these shortcuts through space-time are actually possible. Our own limited exploration capabilities illustrate this challenge vividly. Voyager 1, humanity's most distant spacecraft, has been traveling for over 46 years and has only recently entered interstellar space, having covered a mere 0.023 light-years. At its current velocity, it would take approximately 73,000 years to reach Proxima Centauri, if it were heading in that direction, which it isn't. The energetics of interstellar travel compound the distance problem. Physicist Robert Forward calculated that accelerating a modest 100-ton spacecraft to just 10% of light speed would require energy equivalent to the entire United States electricity production for about 100 years. The energy requirements increase exponentially with speed, making relativistic travel extraordinarily resource-intensive even for hypothetically advanced civilizations. Radio communications face similar challenges. The inverse square law dictates that signal strength decreases with the square of the distance. A transmission from a civilization 1,000 light-years away, relatively close in galactic terms, would be 1 million times weaker than the same signal broadcast from 1 light-year away. As astronomer Jill Tarter of the CTI Institute has pointed out, this means we can only detect extremely powerful signals or relatively nearby transmitters with current technology. The time scales involved in cosmic communication create additional barriers. Any dialogue with a civilization even 100 light-years distant would involve 200-year gaps between question and answer. Such constraints make meaningful conversation effectively impossible. As astrobiologist David Grinspoon suggests, this could explain why civilizations might eventually abandon broader interstellar broadcasting in favor of focused, targeted signals or entirely different communication strategies. The timing problem extends to evolutionary timescales as well. Paleontologist Peter Ward notes that technological civilizations might be common across the galaxy, but separated not just by space but by time. If technological phases typically last only a few thousand years before civilizations either collapse or transform beyond recognition, then the window for overlap between communicating civilizations becomes vanishingly small against the 13.8 billion year age of the universe. Astronomers Jason Wright and Michael Garrett have calculated that even if our galaxy contained numerous technological civilizations, the combination of spatial distance and temporal misalignment would make detection extremely unlikely without dedicated, millennium-spanning search efforts far beyond our current capabilities. Our limited search efforts to date further contextualize the distance barrier. Despite popular perception, humanity has performed only limited searches of the cosmic radio spectrum. Astronomer Seth Shostak estimates that all SETI searches combined have examined less than 0.001% of the Milky Cross limited frequency ranges and time periods, comparable to searching for oceans by examining a single glass of seawater, alas of Sata. The cosmic distance barrier may be temporarily insurmountable, but it isn't necessarily permanent. Theoretical physicist Freeman Dyson proposed that sufficiently advanced civilizations might eventually build light nets, spanning significant portions of their star systems to capture and utilize all stellar energy output. Such massive engineering projects would create infrared signatures potentially visible across thousands of light years, potentially overcoming the distance barrier through sheer scale. More speculatively, physicist Michio Kaku has suggested that truly advanced civilizations might develop technologies to manipulate spacetime itself, potentially creating detectable gravitational wave signatures or other exotic phenomena that propagate differently than electromagnetic radiation. Such civilizations might eventually overcome distance limitations through means we cannot yet imagine. As you drift into sleep, contemplate this possibility. The stars may harbor countless civilizations engaged in their own struggles, triumphs, and philosophical discussions about cosmic loneliness, all separated from us not by absence of intelligence or technological immaturity, but by the simple, unyielding mathematics of cosmic scale. The silence we perceive might be merely the silence of distance, the inescapable consequence of evolving intelligence in a universe where the spaces between stars form chasms that even light requires years, centuries, or millennia to cross. Perhaps someday, with patience and technological advancement measured in centuries rather than decades, humanity might finally bridge these cosmic distances and discover that we were never truly alone, but merely too far apart to hear each other's voices across the strewn void. The signal leakage problem. In the cosmic symphony of potential alien communications, Earth stands as both performer and audience, emitting our own technological noise while straining to hear similar whispers from distant stars. Yet there's a profound irony in our search that may explain the eerie silence. We're listening for something that advanced civilizations might no longer produce: unintentional signal leakage. The signal leakage problem hypothesis proposes that technologically mature civilizations rapidly evolve beyond the brief phase of radiating easily detectable electromagnetic emissions into space. This transitional period of noisy technology might last only a century or two, a mere eye blink in cosmic time, before efficiency, economics, and technology drive them toward communication methods that leave minimal detectable footprints in the cosmos. Consider Earth's own technological trajectory. In the 1930s, powerful television and radio broadcasts began radiating omnidirectionally into space, creating an expanding bubble of electromagnetic signals now reaching roughly 100 light-years in radius. Early Cold War radar systems were particularly powerful, with some capable of being detected across significant portions of our galaxy with sufficiently sensitive equipment. Yet even within a single human lifetime, this unintentional leakage has begun dramatically decreasing. As telecommunications engineer Frank Drake, founder of Modernist T, observed, Earth has grown progressively quieter to distant observers since the 1980s. Our transition from high-power analog broadcasts to digital transmission, fiber optics, directional beaming, and efficient signal encoding has reduced our electromagnetic footprint by orders of magnitude. Communications satellites now use tightly focused beams aimed at specific Earth locations, rather than broadcasting omnidirectionally into space. The economic and technical advantages of such efficiency are overwhelming. Why waste energy broadcasting into empty space when your audience is on Earth? This same economic logic would likely apply to any technological civilization, regardless of their biology or specific evolutionary path. Physicist James Benford has calculated that Earth's radio signature has decreased so significantly that our planet would already be undetectable to civilizations using receiving technology comparable to our own beyond just a few light years. Only deliberate high-power transmissions like planetary radar or specialized broadcast messages would be detectable across interstellar distances. And these represent a tiny fraction of our total electromagnetic emissions. This trend toward invisibility accelerates with technological advancement. Quantum communications, neutrino messaging, and gravitational wave techniques, all in experimental stages on Earth, could someday enable completely undetectable communications from the perspective of distant observers. As science fiction author Arthur C. Clarke noted, any sufficiently advanced technology is indistinguishable from nature. Perhaps advanced civilizations communicate through means that perfectly mimic natural phenomena. The time window during which a technological civilization produces easily detectable leakage might be extraordinarily brief. Perhaps just 100 years out of potentially millions or billions of years of a species' technological development. Astronomer Nikos Prantsos has called this the leakage window paradox. If most civilizations quickly evolve beyond electromagnetic leakage, the probability of detecting any civilization during this brief phase becomes vanishingly small. CTI pioneer Dare. Jill Tarter has compared our search for alien signals to dipping a glass into Earth's oceans to check for fish. Given the temporal brevity of detectable emissions and the vast spatial distances involved, our current search efforts may be fundamentally inadequate by many orders of magnitude. We may need to monitor millions of star systems across thousands of frequencies for decades or centuries before having a reasonable probability of success. Some researchers have proposed that rather than unintentional leakage, we should focus on detecting deliberate beacon signals, powerful transmissions specifically designed to be noticed across interstellar distances. However, maintaining such beacons would require significant resources sustained over long time periods. raising questions about the motivations that would drive advanced civilizations to make such investments. Astronomer Michael Garrett suggests that truly advanced civilizations might utilize extremely efficient communication methods that operate near the thermodynamic limits of information transfer, producing waste heat barely distinguishable from natural cosmic background radiation. Their communications might be encoded within patterns that appear random or natural unless observed with precisely the right analytical techniques. Cosmic steganography, hiding messages in plain sight. Our own rapid technological evolution provides a template for understanding this problem. Consider that in just the past 20 years, humanity has dramatically shifted from broadcast television to streaming services, from radio to podcasts, from unencrypted communications to end-to-end encryption. Each step has made our communications more efficient and less detectable to outside observers. Extending this trend forward even a few centuries suggests near total electromagnetic invisibility. Perhaps most sobering is the possibility that our current search methods focus on a communication modality that represents just a transitional phase in technological development. Like searching the galaxy for EGRIF signals long after advanced such civilizations have moved beyond sign-priv evidence of primitive technology. Fesh-priv technology. Physicist Freeman Dyson proposed that truly advanced civilizations would eventually rebuild their stellar systems into massive energy collection structures, now called Dyson spheres, to harness their stars' entire energy output. These would emit waste heat in the infrared spectrum rather than the radio frequencies we focused most ETI efforts upon. A reminder that our search parameters may be fundamentally misaligned with the signatures of advanced technology. As you drift towards sleep, contemplate this possibility. The silence we perceive might not indicate cosmic loneliness, but rather our search for a form of technological expression as fleeting as childhood. A brief developmental stage that all technological civilizations quickly outgrow. The mature technological species of our galaxy may surround us even now, their communications indistinguishable from cosmic background, noise, or natural phenomena. Their efficient technologies leaving minimal detectable traces as they communicate through means we have yet to discover or even imagine. The silence of the stars may not be absence, but simply conversations conducted in languages we haven't yet learned to recognize. The wrong medium theory. What if the cosmic silence we perceive isn't because no one is speaking, but because we're listening to the wrong channel? This elegantly simple explanation for the Fermi Paradox suggests that our search for extraterrestrial intelligence may be fundamentally misaligned with how advanced civilizations actually communicate across the vast distances of space. The wrong medium theory proposes that focusing our search efforts on radio waves and electromagnetic radiation represents a parochial bias based on our own brief technological history. It's as if we're searching for smoke signals in an age of quantum communications, looking for a technology that may represent just a momentary phase in a civilization's development. Radio waves, while excellent for certain purposes, suffer from significant limitations for interstellar communications. They spread according to the inverse square law, meaning their strength diminishes rapidly with distance. Even powerful transmissions become virtually undetectable against the cosmic background radiation after traveling just a few hundred light years, a tiny fraction of our galaxy's 100,000 light-year diameter. As physicist Paul Davies notes, we're looking for what we can detect, not necessarily what aliens would logically use. Consider our own technological trajectory. Heinrich Hertz demonstrated radio waves in 1887, and within a century, humanity had already begun transitioning to more efficient communication methods. Fiber optics, which use light contained within physical cables, have largely replaced radio for long-distance terrestrial communications. Quantum entanglement experiments now suggest possibilities for instantaneous information transfer across arbitrary distances, theoretically circumventing light speed limitations altogether. Astronomer Anne Crawford has suggested that advanced civilizations might utilize neutrino communications, particles that pass through ordinary matter with minimal interaction. While technologically challenging for us, neutrino beams could theoretically enable communication through the densest regions of space without significant signal degradation. A civilization even a few centuries ahead of us might consider neutrino beams primitive compared to their standard technologies. Gravitational waves, only recently detected by human instruments, offer another potential medium. These ripples in spacetime propagate unimpeded through the densest cosmic structures and could theoretically carry encoded information. Physicist Avi Loeb has proposed that advanced civilizations might manipulate binary black hole systems to generate gravitational wave patterns as communication channels. A technology far beyond our capabilities, but per civilizations or millions of years and thousands, potentially routine millions more advanced. Some researchers have suggested that exotic physics beyond our current understanding might enable instantaneous communication across arbitrary distances. Theoretical physicist Mikio Koku has speculated about the possibility of wormhole-based communications that could bypass space-time limitations entirely. While speculative, we should remember that our knowledge of fundamental physics remains incomplete, particularly regarding quantum gravity and the nature of space-time itself. The wrong medium theory gains credibility when we consider historical analogues. Native Americans could perceive approaching European ships long before detecting radio transmissions. Indigenous Australians would have had no concept of telegraph communications, despite their sophisticated knowledge of the natural world. Similarly, our current search methods may be unable to detect the routine communications of advanced civilizations utilizing physics we haven't yet mastered. A CTI pioneer Jill Tarter has acknowledged this limitation, noting that our search efforts represent very thin slice of potential communication technologies. The radio spectrum contains billions of possible frequency channels, and we've examined only a tiny fraction of them for limited durations pointed at a small selection of stars. Add the possibility of completely different communication media, and our search becomes comparable to examining a single glass of ocean water to determine if Earth contains fish. Astronomer Seth Shostak has proposed that truly advanced civilizations might utilize forms of communication that are engineered to be undetectable except to intended recipients, perhaps using quantum encryption or precisely targeted neutrino beams. Such communications would be invisible to our detection methods by design, creating the illusion of an empty cosmos despite potentially bustling interstellar conversations. The wrong medium theory connects with philosopher Thomas's concept of paradigm shifts in science. Just as Newtonian physics seemed complete until Einstein revealed deeper underlying principles, our current understanding of communication physics may represent just a preliminary framework that will eventually be supplanted by more comprehensive theories enabling forms of information transfer we cannot currently imagine. Some proponents of the wrong medium theory suggest that technological civilizations might eventually migrate to utilizing the underlying fabric of space-time itself as a communication medium, perhaps encoding inflacume fluctuations or other fundamental properties of reality, perhaps an information of invalidity. Such technologies would be completely invisible to our current detection methods, regardless of how powerful or widespread they might be. The renowned physicist John Wheeler proposed that information might be a fundamental property of the universe, summarized in his phrase, hit from bit. If information is indeed fundamental rather than emergent, advanced civilizations might develop communications technologies that manipulate this underlying informational structure of reality, something our current physics provides glimpses of but cannot yet fully describe or exploit. As you drift towards sleep beneath the seemingly silent stars, consider this possibility. The cosmos may be filled with conversations occurring all around us, conducted through means we haven't yet discovered. the apparent emptiness might be an illusion created by our technological immaturity. Like a child who, finding no letters in the mailbox, concludes that no one is communicating anywhere. The great conversation of galactic civilizations may be conducted through whispers in dark matter, encoded patterns in gravitational waves, or manipulations of quantum fields that our instruments cannot yet detect. Our cosmic loneliness may be not a fact of the universe, but merely the temporary condition of those who have not yet learned to listen correctly to the symphony of intelligence that surrounds us. The alien timescale problem. Throughout Earth's 4.5 billion year history, technological civilization has existed for a mere instant. Perhaps 200 years of radio capability within expanse of time so vast that it defies intuitive comprehension. This temporal mismatch may provide one of the most compelling explanations for the apparent silence of the cosmos, the alien timescale problem. This hypothesis suggests that intelligent alien species might operate on temporal rhythms, so profoundly different from our own that meaningful detection or communication becomes nearly impossible, even if they're actively transmitting. The fundamental biological, psychological, and technological timescales of an alien civilization could render them effectively invisible to us, not through absence or concealment, but through temporal incompatibility. Consider the potential diversity of alien consciousness. On Earth alone, different species experience time at radically different rates. Studies have shown that small animals like flies perceive time passing more slowly than larger mammals. A fly's neural system processes visual information at a rate makes our movements appear sluggish from their perspective. At the other extreme, large creatures like whales and elephants may experience time passing more rapidly. These variations emerge from differences in metabolic rates, neural processing speeds, and sensory apparatus among Earth species, all sharing the same evolutionary history. Astrobiologist David Grinspoon points out that even minor biochemical differences could produce intelligence operating at time scales, orders of magnitude different from our own. A civilization based on silicon rather than carbon might process information thousands of times slower than human brains, perhaps taking decades to formulate what we would consider a simple sentence. Alternatively, beings with superconducting neural analogues might think millions of times faster than humans, their entire civilizations rising and falling in what would register to us as a single afternoon. The commutative implications of these temporal mismatches are profound. A message from a slow civilization might be transmitted over centuries, appearing to our instruments as random background radiation unless monitored continuously for decades. Conversely, a fast civilization might compress centuries of communication into microsecond bursts that our equipment would either miss entirely or dismiss as momentary cosmic static. Theoretical physicist Freeman Dyson has suggested that even communication attempts between temporally mismatched species might be fundamentally futile. A civilization operating 1,000 times slower than humanity might spend their equivalent of decades composing and transmitting a greeting that would appear to us as a random millisecond, long burst of noise. Our reply, though seemingly prompt to us, would arrive thousands of years into their future, long after their civilization might have transformed or vanished. Even without biological differences, technological evolution could create similar temporal gulfs. Computer scientist and futurist Ray Kurzweil has proposed that technological civilizations might eventually upload their consciousness into computational substrates, potentially accelerating their subjective experience by factors of millions or billions. To such entities, 1,000 years of cosmic time might pass as subjectively as a few minutes does for humans. Astronomer Seth Shostak has noted that this time-scale problem creates a serious detection challenge for STI researchers. Our search protocols typically scan each target for brief periods, making multiple quick observations rather than continuous monitoring. If alien transmissions follow temporal patterns radically different from our expectations, perhaps broadcasting for one day, every century. Our intermittent observation strategy would almost certainly miss them. The time-scale problem extends beyond communication to detection of artifacts and technosignatures. Paleontologist Peter Ward has observed that even on Earth, technological civilizations might leave surprisingly few long-term traces. After just a few thousand years, most human structures would crumble away, with only the most massive stone monuments remaining visible. After millions of years, a brief period in geological terms, even these would likely disappear through erosion and tectonic activity. This suggests a troubling possibility. Unless technological civilizations undertake deliberate, planet-scale engineering specifically designed for multi-million-year durability, their physical presence might leave no detectable traces after geologically short timeframes. A civilization that flourished for 50,000 years but disappeared 10 million years ago might leave no evidence whatsoever for our telescopes to discover. The inverse problem is equally challenging. Recognizing alien megastructures or engineering that operates on time scales far exceeding human civilization. Physicist and science fiction author Stanis or Lem proposed that truly advanced civilizations might undertake engineering projects spanning millions or billions of years. Such activities might appear to us as natural phenomena simply because their time scale exceeds our ability to recognize purposeful change. Some astronomers have suggested that peculiar astronomical phenomena like Boyajian's star, Kaisi A462A52, which displays unusual, non-periodic dimming patterns, might represent megastructures being assembled on millennial or longer time scales. The irregular timing would appear random to human observers, but might follow a pattern meaningful to the builders, operating on vastly different temporal rhythms. Perhaps most profoundly, the alien time-scale problem suggests that even simultaneously existing civilizations might be effectively invisible each other due to what philosophers call temposolipsism, the inability to perceive consciousness operating at radically different rates, like two ships passing in the night, one traveling at a snail's pace, the other at near light speed. Two civilizations might occupy the same cosmic space while remaining perpetually invisible to each other. As you drift towards sleep contemplating the silent stars, consider this possibility. The cosmos may teem with intelligence operating on time scales so different from our own that we are mutually invisible. Some may think so slowly that from our perspective they appear as motionless as mountains, while others may flicker so rapidly that their entire civilizations rise and fall between our heartbeats. The great silence we perceive might not reflect absence, but merely the profound challenge of recognizing minds that experience time in ways fundamentally incompatible with our own brief moment in the cosmic story. The stars may not be silent at all. We might simply lack the temporal perspective to hear their conversations.